Welcome back to the DemystifySci podcast. I'm Anastasia.
Yeah, I'm Michael Shiloh.
And today we are talking again with John Williamson of the Quantum Bicycle Society. We had him and Arnie Ben on the show a couple weeks ago, and when we were finished with that conversation, we realized that we really wanted to go deeper with Dr. Williamson about his origin story, because it's rare that you run into somebody who has been through CERN, who has spent decades studying particle physics, solid-state physics, and who comes out the other side with the conclusion that, hey, something is deeply wrong with the way that we imagine fundamental physics. And so today's conversation is a deeper exploration of everything that Dr. Williamson went through to get to the point where he's able to come up with physical models, physical interpretations of the equations of quantum mechanics and quantum chromodynamics. And so we talk about everything from his work on single electron transistors when he was working at Philips, to the work that he did when he was working at CERN and starting to get a sense of what was wrong with particle physics, everything that he's been doing with the Quantum Bicycle Society. We discuss the difficult nature of time. We talk about the physical interpretation of spin and charge of the electron, and just overall get this glimpse into the mind of someone who has spent their life really working hard on some of the most difficult and esoteric questions, and has come down on the side of simplicity. At the end of our conversation, he says something which we resonate with really deeply, which is that there is no way that the most true thing that we can say about nature is as complicated as the physics is right now. What we search for is simplicity, because simplicity is what is going to allow us to build something positive and powerful in the future. And that's what they're working on. That's what we're working on. And it was a fantastic conversation. We're planning to have another one next week where we dive into the specifics of how things got so wonky and how physics went off into the mist. We want to have a conversation about cosmological questions, various interpretations of dark matter, and things like that. And so there's a lot left here, and we're gonna keep driving at it. But I think you're really gonna enjoy this. It was a good conversation.
He really is careful in responding to new ideas, and this is something that's been really difficult for us in talking to academics a lot of the time, because you'll put a new idea in front of them and they'll immediately say no because it's not what they learned it to be. And it takes a while of going back and forth where you're like, no, I'm just like looking at the same thing as you're looking at a little bit differently. And eventually you can usually get people to at least not be shouting down your idea. But, you know, Dr. Williamson has no problem saying if he disagrees with something, but at the same time, he has this really wonderful openness to new ideas and
humility.
Yeah, it's just incredible. And if all scientists could embrace that spirit, I think that we'd be a lot further down the road. If you enjoy the conversation, please leave a comment, share the podcast with somebody that you know who might enjoy it. And if you're really loving what we're doing here, you can support us at Patreon, where we're at patreon.com/DemystifySci. And every dollar that we're getting is going back into this program, and we're trying to build it into something that is self-sustaining and allows us to actually contribute to projects rather than just catalog them at this podcast.
Because we are just two people, and we cannot solve all of the open scientific questions in the world. We don't want to solve all the open scientific questions in the world. What we want to do is we want to have a place where people who are interested in solving them can come together and can get funding. And so this is still very small right now, but the money that you put into us through Patreon is going to be money that is put towards building an institution that supports projects that are making the world a better place. And so consider joining us at patreon.com/DemystifySci. And if you can't do that, that's totally fine. Tell your friends, leave a comment, help us with the algorithm. Any little thing that you can do to show your support, if you like it, is plenty for us. And so thank you for listening. Thank you for telling your friends. Thank you to all of our incredible patrons. And enjoy the conversation with Dr. John Williamson of the Quantum Bicycle Society.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
But in my youth, I did a lot of tramping, where I just spend months just living outside, and absolutely absolutely wonderful feeling. It was one of the most. I spent 6 months at one stage just doing that, and it was one of the most life-changing periods in terms of really clarifying exactly what I wanted to do, because I actually dropped out of university after my second year, and this was during the interim period of time, and simply spent 6 months during the summer. Actually, it was a very pleasant time of year. It's not a nasty time of year to be sleeping out. Just traveling around Europe, mostly France and Italy, and living on very, very little, and sleeping and catching stuff and sleeping wild. It just brought me back to the realization of what I wanted to do, which was to understand nature, and the journey from then on, and then 2 more years of university before the thing I told you about last time, which is the revelation in the university library in London. But
yeah, was that all? That was. Did you take any time between undergraduate and deciding to go and get your advanced degree?
No, I didn't, because in fact the advanced degree itself was a bit of an adventure. It was sponsored from Britain, but my PhD was carried out in Switzerland. So I spent the 3 years of my advanced degree at CERN. And that was also a revelation, in fact, because, of course, Britain's a first world country, but in those days, Switzerland was even more so. Switzerland was another step further as well. We're looking at something that was quite a lot richer than Britain was, and it was a revelation to see and to feel being a foreigner. Because, of course, one's really coming from Britain. You have a worldview which is pretty strong. It's especially from Scotland. Scotland's never been conquered. It's always been, the border only moved 30 miles in 1,000 years, so it never moved anywhere. Whereas countries in Europe move all over the place. And you have this very, very strong feeling of it's not really superiority, but it's a sense that this is that this is a place which has always been and always will be, and this is the center of the universe. As a child, especially growing up, you have that feeling. But then to go somewhere where you are a foreigner, and you're a relatively poor foreigner as well, and the people around you are very rich, and you see a little bit of what it looks like from the other side to be not a refugee. It wasn't a refugee in Switzerland, but nonetheless, it's a different kind of mindset. You're looking at things from a different perspective. I think that's very valuable as well. And of course, I've moved countries many times, several times. I've lived in Switzerland for many years, but also in Holland for many years, and the mindset there is again very different. And the kind of things that people find important, and the kind of things that people find totally unimportant, are also extremely interesting. In Britain, a lot of stuff it's not upfront, it's not out loud, it's kind of just things that one takes as something that's understood. And in Holland, everything is completely upfront. People are much more straightforward. In Britain, you can say very nice things to people, but in fact, really be having a sub-message going on as well. In Holland, that sort of thing doesn't happen. If people want to say something to you, if they want to say they don't like you, they say, "I just don't like you very much. Why don't you just go?" That's the end of that.
That's interesting. I thought that was an American feature, but it turns out the Brits started it.
Oh well, no, it was, that's the Dutch who do that. The Brits would never dream of doing anything like that.
No, I meant the keeping it close to the vest, how you actually feel.
Yeah, there's
that's it. Yeah. No,
Well,
sorry, you're going to...
I was going to say that's something that in my family has always been a particularity of Americanness. There's a Russian word, лицемерие, which is like, it's almost like fake facing. Or no. It translates to face metering, where you're never quite allowing the reality of your emotions to come through, and that's most obvious in service work, because there's a service culture in America of the smile and the small talk and the
I'm very excited to share our new offer with you. It's like, are you really excited?
And
how could you be very excited about that, sir?
And that service culture does not exist in Soviet Russia or the former Soviet bloc. It's a thing that to come here and to see it is stunning, because I think that for an immigrant, you look at it and you realize just how foreign of a land it really is to like the very, very depths of the society.
Yeah.
Were there a lot of other foreigners at CERN when you went there?
Oh, goodness gracious me, yes. I mean, our collaboration, European-UN collaboration, was one of the biggest. So I think there were 10 different nationalities just within the group. And the thing about CERN is it had a charter which allowed everybody, including, at this stage, this was back in 1979, 1980 when I first was there. This was still before the fall of the Berlin Wall, but anyone could come. So the Russians were welcome, the Chinese were welcome, everybody was welcome, and all of those nationalities were very strongly supported. The Russians put a lot of money to supporting their people in there, for example, and we had Russian collaborators, and these were wonderful guys. They fantastic humor, really friendly people, really good people, and really quite a contrast to some other folk that were wandering around at CERN who kind of didn't speak English and did a lot of photocopying. So it was two different sorts of people, but everybody was there, all nationalities. So it's very interesting also to compare notes on. We were all nearly most of us were physicists or electronic engineers or from that side of science. But it was very interesting to see what had been taught to different nationalities as well, which areas had been looked at. So in the sort of British and Northern European nations, there was a lot of experimental science that we carried out. We'd done experiments, we had labs. It wasn't really the case for the Russians. Everything was theoretical. And the way that people looked at things and had been taught to look at things in science was very different for the different nationalities. The Russians were fantastically advanced on calculation and on the mathematics. And the Germans were much older than the Brits were, different ages as well of people doing PhDs. British PhD starts at about 21 years old. And the Germans were starting in the late 20s, and the Germans were getting a salary for this. So very different nationalities and very different perspectives and very different ways of doing things, which makes for an incredibly powerful intellectual atmosphere, of course, having different nationalities eating together.
Yeah, that's kind of the dream, actually, that science could be so collaborative from so many different ideas. By the way, was this when was CERN established? Was this very early in the project, I assume?
No, it wasn't that early.
Okay.
No,
okay.
It had been around for quite a long time before. I'm not sure when it was started, but it had been around for a long time before.
Okay.
And this was just after the SPS, the super proton synchrotron. The big tunnel had been. The EMC was one of the big experiments on the new super proton synchrotron. So that was fairly recent, but there had been the intersecting storage rings before that. So no, it was quite far into the project, but it was a very good time to join CERN because there was suddenly this huge jump in energy. So we had a whole new area to look out and to do science in. A very hopeful time. As I say, I was sorely disappointed with the fruits of that labor in terms of what we could do for testing the then theories of, and still extant theories of the strong interaction. And
did that hope slowly erode? Like, what was it like when you first showed up? Were you able to jump on a bunch of different projects, or how did you get time on the accelerator? What was the process like of people doing their experiments or bringing experiments to the table? And what happened before you lost faith? Let's look at this situation initially.
Bringing experiments there are a long time in coming. You have to build a machine which will look at a particular area of science. And so you make a proposal. So groups would form beforehand, before the accelerator was even built, and start designing and building the experiments for that area. So when you came into this, the thing was very mature. There was already an accelerator. There was already a spectrometer sitting there, which could look at the particles which were coming down the line. And there was a huge group, a large group, I suppose. They're now huge, but then they were large, of maybe 30 or 40 scientists, RAs, professors from various universities coming in and out, especially there during the summer and the period they weren't teaching, and young students like myself coming in. It was overwhelming at first because these experiments are gigantic. They're as big as they're as long as a street. The spectrometers 3 stories tall that we're working on, the European Muon. They're even bigger now. So, and what you do is you fit into some area of that, and you go into some area of expertise, which will be a very small part of the whole. So experiments that were going to be done had already been thought about, and you'd come in and, as a young student, what can we get this chap to do? Well, what can't we do? And in those days, it was nobody really knew anything about computers, because computers hadn't existed up until computers were big things that existed in a city, not your city. When the first computer I ran anything on was in Dundee. We had to travel to a different city and punch cards into this thing. And the stuff we were working on at CERN was stuff like PDB-8s and PDB-11s, which are still programmed by using switches. So that was stuff that the older guys didn't know anything about. So you were instantly an expert on software and computing, simply because that was the area that needed some attention. So my jobs at CERN were twofold. One was looking after something called a lead glass calorimeter. It was a total energy calorimeter. Looking for missing energy in electromagnetic showers and so forth. That was one side of it. And then the other side of it was developing programs to analyze data. So this data would come in, and we'd analyze it with some pretty big pieces of software written in Fortran in those days. So one was really looking at quite a small part of the whole thing, a small part of the spectrometer, one element of the I was lucky, I suppose, in that I was doing both hardware and software. So some people were just on hardware or just on software. So I was looking at both. And of course, I was very interested in physics as a whole, so trying to learn as much physics from the people, from the excellent people who were there as well, as was possible in the meantime as well. So 3 different aspects to it. But working on small parts of that. So my job was to have a look at or one of my jobs was to have a look at the difference between mu plus and mu minus scattering. So I developed a program which was part of something called a Monte Carlo program. So what you have is you have the theory, and theory is a strong interaction theory and electromagnetic interaction theory. And then you have the experiment. And what you try and do is you try and see if theory matches experiment. And the way that was done was to implement the physics in terms of a set of computer programs and do simulations of those computer programs. My part in this was to simulate the lead glass calorimeter. And so I wrote some. So I developed a module which became part of a larger module which simulated the whole apparatus, the response of the whole apparatus. So you'd be working with a group of people who are also working on software with that. And then on the other hand, you're working on the hardware and building the next generation of things as well. So
is there someone who at CERN has a grip on the 30,000-foot view?
Yeah, are you guys getting together weekly and chopping it up with the different people that are working on each one of the little modules?
Yeah.
How do you put the whole big picture together?
It's an absolutely wonderful, the best possible organization. It's an adhocracy. So what you simply do is you just get together with guys. People pile in if there's any kind of problem. People will help one another. You're meeting these guys for lunch. The way the experiment was run is you have shifts. You have 3 shifts a day. You have a day shift, a back shift, and a night shift. And you have a group of people on these things. There'd be a rota where you ran through these things. So you'd be working with different people all the time. So you had these opportunities very often to sit down and just, the night shift would be 2 people. The day shift could have 20 people piling in. So the night shift could be quite an intimate conversation between 2 people, and not much is going on. You're just taking data, making sure everything keeps running. And then the day shift, it's mayhem all over the place. You're pulling bits of equipment out, sticking new bits in. But the way it worked was that people simply formed organic groups and got stuff done. And the result was that at CERN, everything was always ahead of schedule and below budget. Excellent people would simply pile into stuff and just get it done and just do it and have fun doing it. It's an incredibly exciting and beautiful atmosphere and a fantastic place to work. Bit of a shame about the physics that comes out of it, really. But these are excellent folk, and they pile in and do great things. I had a great time there, but I realised the physics wasn't really going to go anywhere because it wasn't really testable. It wasn't subject to the scientific method, and that was the reason that I left. And I think the people who are working there will also recognise this picture, that they tend to look at a little bit of this thing and not really have the whole overview. There's this tribal thing going on where there's a difference between the theoreticians on the one hand and the experimentalists on the other hand. So the theory group at CERN is an apart group. It's a group apart which looks at all the experiments, of course, and which are the kind of curators of the theory. And the theory is pretty esoteric and it's something which it takes a while to encompass. So the people working on the experiments, the experimentalists, are a different breed to the theorists. And they're the ones that are supposed to have an overview.
But so I'm curious, I do want to know how the physics starts to deviate, but I'm curious if you have people sitting around comparing the model to the data, what could go wrong exactly? Because you said that your job is essentially to make these Monte Carlo, essentially animations, but mathematical models of what should be happening. And then you look at the data and you try to align the two. What could go wrong?
Well, I think what goes wrong is the fact that in the Monte Carlo, that the base theory has a lot of free parameters.
I see. So it's squishy.
It's very squishy. And it's not just squishy, it's also some of these parameters, well, they're parameters. You're parameter fixing. So you have a system which as soon as you get to the non-perturbative theories like quantum chromodynamics, you have a system where you have an awful lot of free parameters. You have the masses of the quarks, you have the coupling constants, you have the running coupling constants. So the coupling constants are roughly, what are they? Alpha Q quantum electrodynamics is 1/137 roughly. Alpha weak varies, is close to alpha QED, but it has a much higher. It has a mass parameter in it as well, and that mass parameter means that it really kicks in properly only at very high energies, because the thing you're exchanging is not a photon, but but it's the W and Z bosons, and these are very massive. So that means that they're really suppressed down at low energies. But that sort of gets stronger and stronger as you go up in energy, and eventually gets up to the same level as the coupling constant for electromagnetism. Alpha strong coupling constant in natural units is about 1. It's close to unity, and there are running coupling constants that go on from that. It's not always just exactly 1. It does change with energy and with Q squared. And
What is a coupling constant?
Right, well, okay, so the coupling constant is something that tells you what the probability of an interaction is. The coupling constant is, so the coupling constant alpha is related to the electron charge. So it's actually proportional to the square of the electron charge. And it's the strength of electromagnetism expressed as a number, that is, as a dimensionless number. So it's how strong is this thing really? So if you want to think about it, you imagine two things could interact. It's like the probability that they do interact per cycle. So they both, I'd like to interact. But then that only happens 1/137 of the time in electromagnetics. So it's a measure of the electron charge. So it's related to the electron charge.
But is that empirically determined, or is that a prediction of the theory exclusively? Like,
it's not a prediction at all. No, it's something which one takes from. In fact, in quantum electrodynamics, what one does. Let me explain a bit about quantum electrodynamics then. This is the theory of charge-charge interactions. So what is that theory? That theory is pretty much, first of all, what I just said, that the electromagnetic interaction is intermediated by an electron emitting a photon, and then a charge system. Electron can't emit a photon by itself. It has to be part of a system.
An atom.
So electromagnetic system emitting something and then something else absorbing it. So what's the mutual probability that happens? And then there's a raw number for that. But if you imagine moving something twice as far away, then that probability goes down by a factor of 4 because it looks a quarter the size, quarter the cross-sectional area. So you have this raw probability that something might happen that's expressed by a Feynman diagram, for example. And then you have geometric factors which come in that tell you how likely that is dependent on how far apart these things are. So that gives you the inverse squareness of the thing. Twice as far away goes down by a factor of inverse square. And that's pretty much it. The rest is some fancy mathematics which enables you to do that. So it's the core of the theory is what's the probability that electron A that system A interacts with system B.
So if those constants are being tuned by the experimentation, what's the problem? Isn't it good that it's squishy like that you can tune these constants?
Well, that's not squishy. The QED constant is known to n decimal places. That's not squishy at all. But the way that you make it non-squishy is you say, okay, it turns out that if you just do the maths for that, and I've just been given a copy of Dirac's Quantum Mechanics 3rd edition. This is my copy of the 4th edition, which is a little bit the worse for wear. It's got wet occasionally. It's got lots of notes in it. But I'm just having a look at the last chapter in both of those, which are completely different. This is a magnificent mind trying to make sense of quantum electrodynamics before quantum electrodynamics was really developed in its modern form by Feynman and others. But it's not squishy at all. But the reason that it's not squishy is if the maths is squishy for the thing, but then you say, okay, well, we're doing this calculation, which is pretty much what I just said, and we find that we get infinities. But we know that, so for example, we could try to calculate the electron charge, and what we find that in the theory is that it's negative infinite in the raw theory. However, we know that it's not negative infinite. We know exactly what the value is. So what you do is you say, okay, well, we've got the answer. So what you do is you do a calculation in perturbation theory, and that gives the answer minus 39,426,246 times the electron charge. You say, well, we know it's not that. We know it's really just 1 times the electron charge. So what you then do is you divide everything by 39,000, whatever number I just said, and bring everything down to what's called renormalize everything to the electron charge level. And that's one of the renormalizations you do. So that gives you a fixed point around which you kind of expand. Then the other one you do is you find out that the mass, the mass isn't negative infinite, the mass is positive infinite when you use the theory. So what you do is say, well, we know it's not positive infinite, we know what it is because we can measure it. So you put that in and you do the same thing with the charge and the mass. And pulling those two numbers, getting those two numbers to be correct in this renormalization scheme by dividing everything by this big number that you get in your particular calculation, means that everything else works as well. So after that, all of your cross sections, all of your numbers, G minus 2, the anomalous magnetic moment of the electron, all of those things you can calculate on that basis. That works for quantum electrodynamics beautifully, and you can get n decimal places. There's an awful lot of truth in that theory. The problem comes when the coupling constant that works because the coupling constant is quite small. So quantum electrodynamics isn't squishy at all. It's it's possible to calculate things very, very accurately. That's not the case with quantum mechanics.
I just want to say that's the best explanation I've ever heard for renormalization. I really appreciate that. That made it pretty clear for me.
But you're saying that that's not the case for quantum chromodynamics.
No, it's not the case for quantum chromodynamics because the coupling constant's approximately 1. And what it means is, in quantum electrodynamics, if you want to calculate a process, you calculate the base process, which is single photon exchange, but then you calculate radiative corrections to that. So in a process where something hits something else, where something bounces off something, which is what you're trying to do in the theory to match what's happened in the experiment. The thing is that there are other terms that come in that one needs to correct for. In Feynman diagrams, these look like a vertex correction could be an electron comes in, it bounces off, and it emits a photon, and that does something to a particle below it. But that incoming electron can emit a photon which is absorbed by the outgoing electron, so the photon bounces across to it. That's a radiative correction. Now, in quantum electrodynamics, those terms, there are several of these. There are ones where the virtual photon that's been exchanged could form a virtual electron-positron pair. So you get a photon, virtual electron-positron pair, photon, then the vertex. That's another one needs to take into account, which is a low-order term. In quantum electrodynamics, those terms are quite small. And so after you've calculated the first and second-order terms, you're really down to loads of decimal places. You don't need to go further. In quantum chromodynamics, because the coupling constant is much larger, those other terms are also as large as the initial term, and there are more of them. So what you do is you can't calculate with it because you can't do a straight calculation, and the renormalization scheme doesn't work. So what you do is you truncate it. You just make up a truncation thing which fits experiment, and that's one of the things you can do to make the damn thing fit experiment, is just choose where you cut off. That's one of them. That's the most primitive one, really, but that's one of the things you can do. So it's squishy because it doesn't really give you it can't give you numbers. You can try and, given the experiment, you can say, okay, this set of numbers is consistent with all the experiments we know. You can use it to parameter fit, but you can't use it to predict. At least the experience has been that when you try and use it to predict, you get it completely wrong.
That's fascinating. Yeah, I did a lot of curve fitting in my own doctoral work, and it's very interesting. I mean, we ended up essentially deciding on a window that we would apply to all of our data, right? So that we would have it be consistent across the board. So no matter what time constant we're reporting, at least it's consistent from experiment to experiment. But it sounds like what you're saying is that you can adjust this cutoff value for each experiment separately to kind of get what you want out of it.
It's not the only parameter one plays with, but that's one of the primitive ones. The thing in quantum chromodynamics is you've got a lot of parameters to play with, and you've got enough that it has proven so far to fit all sorts of. But it's not just quantum chromodynamics. You've got other non-preservative theories like most of the string theories as well, and there are dozens of these things, and none of them can be excluded on the basis of experiment. So they're all consistent with experiment, which means they're all equally valid or invalid as the case may be.
So let's talk about when you first started to get cold feet when you were working in this system, and was this the first thing that kind of tipped you off that maybe this wasn't the best way of going about things?
Yes, this was the first thing that tipped me off was the fact that we didn't seem to be able to test the theory experimentally. So then I thought, well, what are we doing? What are we doing all this stuff? If we can't test it, then what's this about? And but it wasn't just that. There was also something else. There was also Krish's group, the zero gradient ZGS people at Argonne National Laboratory. They had looked at polarized proton spin. This is an experiment I wasn't involved with, but I knew some of the people in it, or had been in it. It's quite a small community, the high-energy physics community in a way, a big village. And Krish's group in 1977 had measured polarized proton scattering on polarized proton scattering. And what they observed is that this should be a strong interaction. So you've got two protons hitting one another, and then fragmenting, and then scattering. And they're looking at the total cross-section for that scattering. What they found is that the cross-section for spin parallel scattering in one kinematic regime was 4 times bigger than for spin anti-parallel scattering of. Now, that's a spin effect. So the model for the standard model for what the proton is, it's a bag of 3 quarks with some gluons and with some valence quarks and with some C quarks in it. So you have up, up, down, and up, up, down. And these quarks, the statistics of these quarks, they have to be fermions as well, is such that if you have a look at the cross-section, so you've got a cross-section spin up, and spin up, spin down. This is 4 times stronger interaction than that is. 4 times stronger. Now, it shouldn't be, because if you look at that in terms of just the 3 valence quarks, what you have to have is you have to have up, up, down spin for the quarks. When you start doing the sums of cross-sections for the individual quarks, which is what you think you have in the standard model, it turns out that some of the scattering probabilities have to be negative to fit the data. And there's a beautiful article on this. The original paper is O'Fallon et al. Pizrev, 1977. But to get a good explanation of this, you can look at Scientific American 1979, May 1979. Krish, the sort of group spokesman, wrote a beautiful article for Scientific American. It just disproves the quark model.
Oh, no.
Now, this is a very serious, nasty experiment that doesn't depend on all of those squishy things. This is really just looking at the cross-section of stuff. And it disproved the quark model. And that was ignored, and it still is being ignored, and has not yet been resolved satisfactorily.
What is the standard justification that's given?
Well, the standard justification is that it's just a problem. It's called the proton spin puzzle.
It's a puzzle.
So it's called a puzzle. Well, that's good. But so you got this puzzle, but experimental science is supposed to overthrow theories that don't fit experiment. That didn't really happen. So people look for explanations in terms of, well, the scattering isn't really with the valence quarks. It's really with the other bits of the proton. Half the proton's doesn't appear to be charged. You have this idea that things held together with gluons as well, and the gluon theory is a non-abelian theory. What it means the gluons interact with one another as well. So, but if the gluons interact with one another, you should be able to form things called glue balls. No quarks, just a ball of glue that sticks together as well. That's perfectly acceptable in the theory. But these things, my name's on a bunch of paper that sort of begins with a search for glue balls in, and then ends up with a negative result of not finding them. So it was that kind of thing as well. The fact that didn't seem to touch it. What the hell is going on when experiment is not doing its job to hold theory to account?
I mean, is this a case where you're on a sinking ship, but it hasn't sunk yet, and there's no replacement, like there's no rescue, no life rafts? In other words,
get the feeling that the mathematics are so complicated, and there's been it's maybe a sunk cost fallacy to extend your sinking ship metaphor.
Well, there's no replacement, right? If there's nothing better
there's no replacement. That's the thing, Michael. You're absolutely right. The fact is this: you can say, yeah, okay, well, it's not right, but then you say, so what is? What's your theory?
That's the problem.
That's the thing. So I tried to go to a different kind of group. I went to Hadron Physics group, where we're looking at proton-proton scattering, because I thought that was a place I might find some more answers. We published some good papers on that, but again, no real answers to the deep question. That was really what stopped. After that, forget about it. It was not going to. You can't measure these things, and therefore it's not that. There is no point in. One has to try and find a better theory. But then the question would be, and the question was to me, eventually during my RA period, my boss, wonderful guy, Norman McCubbin, was very tolerant of letting me look at these crazy John theories as to how stuff might work, and trying to work out if it wasn't quarks, then what was it? What was going on? And he was very tolerant of this and very helpful in a way where I didn't even know he was being helpful. He did some studies himself to look at the theories that I was also trying to puzzle over, and called me into his office one day and said, he'd been looking at this and he'd got piles of stuff as well. And he'd come to a conclusion, which I also knew about, which is that a lot of the kind of theories that I was trying to work with had founded on G-2, on the anomalous spin moment of the anomalous magnetic moment of the electron. And he and I spent a half a day. He asked me the question directly, can your theory account for this? And I had absolutely no idea where it was coming from at that stage. So I had to say no, honestly. So he said, well, in that case, it can't be a valid expert. Quantum electrodynamics does do this, by the way. So I was just so far off the mark with those things when I was working at CERN that I realized that I wasn't capable really of making proper progress on that. And the fact that I wasn't capable of making progress on that, that's what made me decide to leave high energy physics and go into something where I could make some proper impact and do some good. So I did. Switched to solid state physics. But the thing that stopped me was the fact that it was that argument. What will you replace it with? What can you replace it with?
That seems like an unfair question, though, because if you are working by yourself and the entire weight of replacing it is on you, that seems patently unfair, because the other model is being propagated by hundreds, thousands, if not tens of thousands of people. And so it seems like what would make the most amount of the process for being able to change it would require everyone in the room to agree that, okay, this isn't working out, and we have to throw some time and resources at figuring out some alternative.
Task force.
Rather than just looking at the one person who's sitting there and is trying to come up with an alternative and dismissing them when it turns out that their new theory doesn't cover everything.
Oh, no, Norman didn't dismiss me at all. Norman was tremendous. No, but he was being helpful and pointing out. I think he was trying to point out that it was a worthless task because it couldn't too far away from solving this thing without the intellectual power to do that. No, he did me a great service, because it was at that point that I decided that I wasn't going to take up the offer of another job at Rutherford Appleton Laboratory working at CERN and actually go and do something completely different. So that was fantastic help. It wasn't being dismissive at all, and I would never say that. Norman was never dismissive.
Did you return? You returned to those ideas though later.
Oh yes. So yes, I did, very much so. And in fact, the present theory, well, does get G-2. I do understand where it comes from. The blockage has been unblocked. The point from which progress can be made is now there. So, but this is 35, 40 years later. This is 50 years later.
All right. I do want to get into that for sure, but maybe we can talk about where you went to next first, just to keep this kind of linear.
What happened next is my contract was coming to an end. I was offered another contract to continue working at CERN, but I applied for a bunch of jobs. I applied for, I think, 6 jobs. I got offered all 6. So that was fine. One of them was a university lectureship in Australia. Another one was working for ESA. Another one was, but the one I chose for a very simple, because of one guy. And the way it worked is, did I tell the story last time? I don't remember. Did I tell the story about the bread and cheese and ham and?
I don't think so. It can't hurt anyways. It might be a completely different audience listening to this one then.
Well, okay, yeah. No. Well, the thing is that what I did is I arranged job interviews so that I could travel around. And I've been to a job interview in France, and my next job interview was in Holland. And in France, what happened is about 12 o'clock, everybody adjourned to go for lunch. And lunch consisted of a fantastic meal with wine for 3 hours. Absolutely beautiful food as part of the job interview process. So it was a great place. Anyway, got to Holland, and the Dutch system was they were going to interview me for 3 jobs. And I could, if they decided to take me on, I could choose any one of the 3. I loved this. This was Philips. This was a good thing. So I went in and had a job interview in the morning, early-ish in the morning, and then had another job interview later in the morning. And they're both interesting projects, very interesting projects. One of them was working on MRI scanners, I think it was, or very interesting stuff. But then I had lunch scheduled with Andries Miedema, and that's fine. So went into this private dining room, lovely, and there was this lovely guy, about my age now, but I was a lot younger then. So lovely guy there, Andries Miedema, stood up. We shook hands in the Dutch fashion, and sat down. And and it looked very good because there were wine glasses on the table, and there was a great big table. It was all set, and then waiters came in with these silver trays with these big bowls over the top of them. Oh, this is going to be good. And they came to me as the guest and lifted up the bowl. And on the bowl, underneath the bowl, was slices of ham and slices of cheese. And then the other bowl consisted of slices of bread. And the idea was you chose your bread and you made either ham sandwiches or cheese sandwiches, or as a special treat, you could have ham and cheese sandwiches.
How sophisticated.
Unbelievable. But there were a couple other things too. But that was the main course was ham and cheese sandwiches.
I think they still feed that to the grad students at all universities.
Yeah, I had to give a talk in London one time, and the food was remarkably terrible as well. Actually, I went back at one point, and I didn't get enough food at dinner, and I went back, and I was like, could I have some more? And the lady was like, no, we only have 1 fish per person. I was like, oh, come on. Yeah. The rest of it was very brown and it was a very drab weekend of meals.
Yeah, there's some old-fashioned British food. It's about boiled for a week, and it all should be the same colour. Yeah, it's horrible. Luckily, things have changed a little bit. But anyway, that was the system then. But the interesting thing, we didn't really get onto the food, because what was happening instead is me and Andries were just talking physics. We're just talking about different aspects, like we're doing now, just having a chat about physics. And he was very interested. He said, I'm really curious. I want to know why somebody like you is applying for Philips. Planetary physicist, look at your CV. I mean, what do you want to come and work here for? So I told him a little bit of the stuff I've just told you. And we talked about materials, and we talked about devices, and just had a great time talking physics. And at the end of the meal, we hadn't really touched the sandwiches. Not a meal. He said, well, John, I'd like to offer you a job. He said, you can take any of the 3 jobs which you're having interviews for today. I said, hang on a minute, I've only had interviews for 2. I haven't even seen the 3rd guy. He said, doesn't matter, you can take that if you want as well. But he said, but I'd like to offer you a 4th job if you want to take it. I said, oh yeah, okay, well, what's that? He said, well, whatever you like.
Whoa.
And I said, pardon? Well, whatever you'd like to work on, provided it's something which is in the solid state, can lead to devices, can lead to things that are actually going to be manufactured, whatever you like. And one of the things we talked about has been fun. I was saying that it would be interesting to look at electrons in the solid state, because we had spectrum, as a high-energy physicist and a quantum mechanic, that's what I've been doing for 7 years, looking at very high-energy electrons. But you could produce electrons. I knew about the quantum Hall effect and stuff, and high electron mobility transistors and large electron mean free paths. So I thought it would be fun to look at the electrons, same electrons, of course, but now in the solid state, and then put them into beams and then have a look at the spectroscopy of electrons in the solid state. So, well, I'd like to do that. But so I said, but, you know, it could be pretty expensive to produce things like that. I mean, what's the budget? He said, what he said is there isn't any budget. There is no budget.
Oh, no.
It's the budget is unlimited. Whatever you need.
Oh, wow. That's been uttered a series of one times in the history of the universe, I believe.
Yeah. Well, Philips at that stage was making a very large amount of money, and the business model for Philips was that it had turnover, and it made about 1% profit on turnover, but it spent 10% of turnover on R&D. It was an enormous R&D place. Philips Nat Lab had 4,000 employees who were all working on trying to build electronic devices. And look what comes out of it as well. I mean, think about electronic devices in the 60s and 70s, well, or even before that. They're all invented by Philips. Just, you know, what do you want? You know, compact discs. You know. Philips was inventing things, and that was its business model. Its business model was to be inventive and to introduce new things. So they didn't. There was nothing they couldn't afford that I could think of to build a system. So for them, the budget for doing that was money well spent. So that seemed a pretty good deal. You know, do whatever you want with unlimited budget. Well, hey, come on, who could refuse an offer like that? So that's what I ended up taking, and the result of it was the quantum point contact. The result of it was stuff like this. Oh, okay, one of these.
Yeah, usually you have to sign away your soul or something to get this kind of a deal.
Yeah, tell us. So you're showing us these diffuse. The top looks like kind of a diffuse topographic map, and the one below looks like the energy containment
This is a quantum well, and these are quantum wave functions in a quantum well. Here's 1 half wavelength, 2 half wavelengths, 3 half wavelengths, 4 half wavelengths. And this side is the electron density from that stuff. So that's psi star psi squared, the squared density. So the bump up and the bump down go to 2 bumps up. So this side is the electron density. And this is a measure of the quantum conductance in a quantum point contact as a function of the position of the point contact. And look, here you have upside down, here you have the shape of the first wave function, 1 bump, of the second wave function, 2 bumps, of the third wave function, 3 bumps. This is the profile of an electron in the solid state, of single electrons in the solid state.
So basically the shape of an atom, basically the surface of the atom. It's basically if you do a radial, if you multiply this by the cross-sectional area, you end up with the distribution function that essentially gives us the shape of the shells.
Yeah, but this is plus or minus 30 nanometers, 40 nanometers, plus or minus 40 nanometers. This isn't atoms.
It's huge, yeah.
Electrons with wavelengths of roughly 40 nanometers at the bottom. The electron charge is spread out over that size. Electrons in the solid state are that big. They're as big as their quantum mechanical wave functions in terms of an actual measurement of the actual charge over such a quantum point contact. That was a 1990s measurement. But the quantum point contact was discovered before that. This was quantized conductance. This is a big thing. So
let me make sure that everybody grasps that really quickly. So traditionally, the electron should the shell should probably only extend a couple hundred picometers, and you're talking about nanometers. So what is that? Is that a factor of 1,000 bigger, or is that 1,000,000 bigger? It's very, very big.
Yes, it's very big. But you typically a hydrogen atom is about an angstrom across. So a nanometer is 10 angstroms. So 10 nanometers it's 100 to 1,000 times bigger than the electron in atoms. It's the size of electrons in semiconductor materials. So and they get bigger still in pure metal crystals or in superconductors, where where's my silver pen? Hang on a bit.
And they must be overlapping one another to some extent, right? Inside of these conductors at that point.
Yeah, that's
so it's
right.
almost like their shells are kind of joined up in a way.
Well, they're delocalized. So here's a stainless steel pen. The biggest electron in this thing is twice the size of the pen, because what it does, it has a half wavelength vibration here, then a half wavelength, quantum mechanically, then a half wavelength vibration there. So there's an electron there, which you could sort of see as, so its distribution would be kind of like this. Then the next electrons go like this, so that charge distribution goes bumpity bump, and then of course you get bumpity 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 bump. But there's not many electrons like that. The vast majority of the electrons in a metal are roughly atomic sized. So you end up with the surface of this thing really. What I'm touching here is I'm touching electrons. That silvery surface is an electron gas which is reflecting light. So, and what I'm touching here is I'm touching the electronic surface of that beautiful piece of stainless steel.
Yeah, it's really interesting to me that inside of a metal under this free electron model, you have essentially a degenerate electron gas, which is fascinating because people usually think of degenerate matter as being some exotic thing that's found in a white dwarf or something, but it's actually, it also really models just a simple metal at the same time, which is quite fascinating.
Does. Isn't it fantastic? Isn't it amazing? Yeah. So, but the fact that we can actually get into experiments and see that quantum mechanics in sizes that we can get down to, where we can measure the shape and the profile of those electrons, it's utterly stunning. And it's magnificent that the electrons are doing this. We have to understand this is the thing. One has to understand what the electron is. How can anything do that? And what is it that's doing that? And what's spreading out? And how does that work? That's the stuff of the new theory that Martin and I put together over 30 years. And that's what we're trying to explain in the Quicycle group. So how these things work. But this was the start. Well, this wasn't even the start of it. The start of it was back in before CERN and CERN. But this work made our group world famous. So Henk van Houten, Carlo Beeneke, myself at Philips, Bart van Wees, Leo Kouwenhoven at Delft, and Jeff Harris, Tom Fox and Jeff Harris in the UK. We published a series of papers back in the 80s that are still being hugely referenced today. I've had 4 references to one of those papers come in today, just in the email. You have a new reference to this work, and they just keep coming in. Certain ones keep coming in too, but these ones come in at an even higher frequency. It was fabulous work that we were able to do with these. Well, I suppose if you're given an unlimited budget, do what you like.
Yeah, I'm surprised that they encouraged you to publish these findings and they weren't trying to keep them in-house.
Well, in fact, we did have to hold them in-house for a year. We had to write a patent first. That then had to go through before we could publish it. So they were held in-house and they were patented. Patents expired. It's more than 20 years ago.
Can you patent theories, or were you patenting the apparatus, or what was being patented?
No, what was being patented was multi-valued logic based on quantum point contacts. That was one of the things we patented. The other thing we patented was the single electron transistor. So after that, I've got it here actually.
So you patented the method or the process essentially that you.
Yes,
nice.
The method. This was this is the shape of a quantum point contact. The potential. There's that parabolic potential I showed you just now. This was made for me when I left Philips. It was my first calculation of these things. But this is actually a quantum dot. It's the first theoretical. This is a computer model that I put together, and then this has been expressed in aluminium as a going away present when I left Philips of the first quantum dot that we built, which had 4 gates. So that was the world's first quantum dot.
What would the axes represent there? So he has a 3D model of essentially a couple of troughs that are split in the middle by a well.
Well, it's this is this dimension is potential energy.
So the y-axis, let's say.
Let's take that to be the z-axis. Then the x plane is the is a degenerate two-dimensional electron gas, which is formed at the junction of a gas-L-gas heterostructure. So you have
spatial.
Yeah, so the electrons are trapped in the material. What you do is you grow material like licorice. So you grow gallium arsenide. So you grow a lump of gallium arsenide upwards. Let's say it just comes to my glasses. Then you stop growing gallium arsenide and you start growing aluminium gallium arsenide, which has a different band gap. What happens is the electrons in the aluminium gallium arsenide, if you dope that, fall into the interface between the gas and the L-gas gallium arsenide and the aluminium gallium arsenide and form a two-dimensional, quantum mechanically two-dimensional layer of electrons at the interface.
Like an interface that you can visualize, essentially.
That's right. And this is the basis of a HEMT, high electron mobility transistor. What you do is you reduce the dimensionality, that reduces the scattering and increases the mobility, which makes things go faster, which means that you can make mobile phone technology, for example. So you can make the super fast transistors in mobile phones. So this is at the basis of that huge flowering of speed, which enabled the mobile phone revolution that came after that. So anyway.
So are they implementing this technology then in?
Oh, the technology's been implemented. You've got it in your pocket. Well, I've got... it's in these things at the front end of the hard bits are this kind of stuff. And
so how does this relate back to the realization that you had at CERN? So you're doing this in solid state and you're finding these odd behavior.
Well, what it meant is it meant that, with this kind of stuff, you're getting inside the electron. I'm engineering stuff at smaller sizes than the electron. I'm getting to look inside it. How can you do that? What is this thing? It's not a little point particle that everybody thinks it is. It's a great big thing. How? What is the electron? How is it made? What's the surface of it like? What's it like inside? At this stage, I was a new quantum electronics is a bit of a strong statement. I knew of quantum electrodynamics. I knew a little bit about it. I learned it at school, and I knew quantum mechanics in that fairly well. And these devices, to engineer this device, I was using my knowledge of quantum mechanics. I was making something that was quantum mechanically a single electron in the little dip. I don't know if you've seen the little dip in the middle there. Mm-hmm. But that takes one electron at a time. And what we could do with it is we could put one electron in, and then we could tip it out, and then tip another one in. So you could put a voltage from left to right, and you could tip one electron into the thing and then one out. So you could phase lock. You could have a stream of electrons that were phase locked to an AC noise-less single electron source. Back in the late 1980s, that's what we were using it for. Next electron, please, and so forth. These are big. They're great big things. So how can they be both very small at CERN and very big in the solid state, and even bigger in superconductors? How is that possible? How do we explain? How do we understand what these things are?
And so just to clarify, the phase locking allows you to repeatedly measure the same spatial dimensions of something because you're looking at the same moment over and over.
It allows you to have a current which is noiseless. It allows you to eliminate the shock noise. It allows you to count. Well, you don't need to phase lock it. You can just, if you want an electron, you just let one out, and you've got a single electron source. It's a single electron transistor. So an electron working with just one, a transistor working with just one electron. So we painted that too.
At any point, is it possible that the thing that is being studied at CERN is not the same thing that's inside of the transistor?
Well, if you look at the theory, then the way they're described is different at the higher levels of theory. An electron at CERN is described as a thing which has charge, it has spin, it has mass, and that's it. It's a thing, but it's a thing which is a point thing. It's very, very small, but it's got a spin, and the spin is very, very big. So something's spinning, but it can't be very, very small if it's spinning, because it would need to be big enough, even at the speed of light with the mass that it's got, to carry the spin of a half h-bar that it's supposed to have. It would have to be quite a lot bigger. It would have to be pretty much 10 to the minus 13 meters, not 10 to the minus 18 meters to measure that. But on the other hand, when you measure its scattering, it looks as though it's a point charge with 10 to the minus 18 meters. On the other hand, when you stick the same electrons into the atom, bang! They're an angstrom in size. My goodness gracious me, what happened? And you stick them in a solid state, and Williamson and Al can measure the damn things to be 40 nanometers. No, you can measure them all the way up, and they really are, this is an enigmatic object. This is an object for which we, what do people think an electron is? I mean, what's our current view of an electron? It's so primitive, if we don't include the stuff that Martin and I are doing, that it beggars belief that we can get away with thinking about these things as being that simple.
Well, it strikes me that a huge part of the confusion is that the electron is a dynamic object, so that means it's abstracted in some sense, that there's already motion embedded in the concept of an electron. And ideally, bodies should be a static concept that then undergo motion. And so we treat, in some context, the electron like it's a static object that you can move around, but it already has motion embedded in it as a concept. And so there's a great deal of confusion because there's no primary actor there. There's no actual body that's in motion necessarily, because it's already in motion as an actor.
So our job as scientists should be to find out what is inside it, what is moving, what is waving, what's it waving in, how does it operate, what's the dynamics, what's the theory behind that. That's what we need, not some crappy theory where we say the electron's one of the elementary particles and we can know no more about it.
100%.
Bullshit. Of course we can know more about it. We can know more about it, first of all, by measuring it, and then by imagining how that could be.
And so how do you account for the smallness and the bigness of it?
Okay, now this is going to get potentially really technical. But
all right, well, we'll take it as slow as possible. Yeah. Please forgive us if we interrupt you to clarify something.
Interrupt as much as possible. I'll try. The thing is that what one's dealing with is one's dealing not with what I think one's dealing. Sorry, this is now moving on 30 years from the point we're at CERN, okay, and the point where I was doing this kind of thing at Philips. And it's moving on also with a huge amount of knowledge that's been put together between myself and my wonderful colleague Martin van der Mark, who is sadly no longer with us. So I'm really jumping forward an awful long way. So we'll have to perhaps come back again. But let me say what I think is happening. What's happening is that the theory that we had to look at the electron, where the electron is just a bag of numbers, quantum numbers, charge, spin, quantized charge, G-2, lepton number. Each one of those things that you say expresses something which you don't know anything about. It's got 1 unit of electron charge. It's got half a unit of spin. It's got one lepton number of +1. These are numbers which you're ascribing to it, like you've got 1 apple or 1 lump of rock. You know about as much about this as you knew about a lump of rock as a caveman, right? You're just counting the rocks and banging the rocks together. But what you need something which allows the underlying stuff of which describes the underlying stuff of which the electron is made.
Right.
The underlying, whatever that is. Now, this is manifestly true. One needs to know what, just as we know what atoms are made of, that they're made of protons and neutrons and electrons. We don't have that degree of knowledge, or at least mainstream does not have that degree of knowledge about what's inside the elementary particles, what makes them. So what do I think makes them? Well, it's this stuff we talked about last time, the Ur stuff, the square root density stuff. So in quantum mechanics, you say, oh yes, we know the wave function. It's a times e to the I kx minus omega t. So the kx minus omega, so it's e to the I theta, where the phase angle theta is the wave number k. That's the times space. That's 1 over space times space. That's the number. Minus omega. That's the angular frequency times time. Frequency times time. Inverse time times time. That's a number. So that's a phase angle. Kx minus omega t, and it's e to the I theta. A e to the I theta. So that's what a quantum mechanic. That's the quantum mechanical knowledge of what's happening in here. But the question is, what's the stuff in the A of the A e to the I k? e to the I kx is just some maths, which tells you things sort of waves, really. So it's just a wavy stuff. So something is waving. Well, what's waving inside the electron? It's subelectron stuff. Mm-hmm. What is that subelectron stuff? Well, it's got a mass density and it's got a charge density, and this measures the charge density. So the charge density does follow the quantum mechanical prediction. So the charge density does spread the way that quantum mechanics says that it spreads. We can this isn't the only experiment. Mine isn't the only experiment. Obviously, there's been lots of these experiments. So how does it do it? Well, I think the way that it does it is that it is not a solid little bit of stuff. What it is a topology of a flow of some substance, mm-hmm. of some in a wave function, and it's not as simple as e to the I kx minus omega t, e to the I theta, because there isn't only one theta. There's more than one theta in an electron. There are two of them, theta 1 and theta 2. Now, who said that's not me? That's not Williamson. This is de Broglie saying this back in the 1920s, for crying out loud. So if you read de Broglie's thesis, and it's beautiful, it's a beautiful piece of work. His French is just utterly superb. It's utterly lovely. It's the best French I think I've ever read, and that includes except for possibly some of the French poets who are pretty good with words too. But anyway, it's very beautiful.
I think he was a prince or something, right? He was
a prince. He was a prince.
He had a lot of ideal education, I'm sure.
Yeah, that's right. Anyway, there are really two frequencies going on, and you can convince yourself of this without going to Williamson's theory quite easily by thinking, look, if you accelerate an electron, if you go faster, E is h nu. So if you look at imagine the electron as a little clock ticking backwards and forwards, click, 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 like this, an oscillator of some description.
So they're breathing.
Well, let's look at that wave relativistically. If you look at that wave relativistically, if you look at from a different frame, then the waving should slow down according to the atomic law, according to the relativistic law of the slowing down of clocks. Should vibrate more slowly. So as you tick, 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 should slow down. But on the other hand, if you look at its energy, if you look at it from a different frame, its energy goes up according to E is h nu. The frequency law is the energy of an object is given by Planck's constant times its frequency. You add kinetic energy to it, it's going faster. So the frequency of vibration should increase. But it has to both. Now, okay, so the problem de Broglie struggled with is how can it both increase and decrease at the same time? Now that sounds on the face of it as though it's an impossibility, but it isn't an impossibility because you can have two different kinds of oscillation, spatial oscillation, a temporal oscillation, in such a way that, so he discovered this was possible, and it's de Broglie's law of the harmony of phases, which is expressed in the harmony of phases, very important law, which is expressed in his theory.
Yeah, that reminds me of maybe AC phases that we think of in terms of you can have different loads being delivered at the same, subsequently in the same wire or something like that.
Yeah, can you talk about spatial oscillation versus temporal oscillation?
Yes. And in fact, that's what's required. De Broglie didn't frame it in terms of spatial and temporal oscillation. That's me with insight that I now have. But he looked at it in terms of it being two oscillations, and he discovered that it was possible to have two oscillations going on in such a way that at every point in space and for all time, the two oscillations were in phase with one another, but they differed in frequency. They diverged in frequency. At zero velocity, the two things are perfectly in phase and go around with one another. But as you increase the relative velocity with respect to oneself, one of them slows down and the other one speeds up. So, and this is de Broglie's law of the harmony of phases. What he noted is that would lead to an extra apparent oscillation of wavelength lambda is h over p, which may be familiar as the de Broglie wavelength. But the de Broglie wavelength was discovered by de Broglie from relativity, from a proper consideration of relativity. That's what his thesis is about. That's what the early papers are about. Now, you get a lot of argument these days saying, oh, well, it's either quantum mechanics or relativity. They can't both be correct. But it turns out they are both correct. And the oscillations of quantum mechanics arise, lambda is h over p, arises from a proper consideration of oscillations in relativity. So
how has that gotten lost? I'm confused, because that's one of the standard mantras of quantum and relativity.
Potting. Do you know, it took me a long time to find anybody else, any other physicist who even knew about this. Because what we do is we start from lambda is h over p. That's what we learned. That's what the three of us learned in our undergraduate degrees, right? We learned about the de Broglie wavelength, but not the derivation of it, not where it comes from, not that it comes from a relativistic effect. Mm-hmm. Why not? Because it's considered too hard. When you meet it for the first time, you simply meet it as a principle. We're getting too many damn principles and too much explanation of where the principles come from.
What is the significance of its origin from relativistic effects?
Yes.
Just that it's consistent across the board? Or?
That it's necessary that there are two. That there have to be two oscillations. And these oscillations are in phase harmony with one another. That is, there's one slower oscillation, one faster oscillation, in such a way that at any point in space-time, the two oscillations are in phase with each other. So if you look at a particular place in space and time and you find one's at 86.3 degrees, then the other one will be 86.3 degrees. It's just that one of them will be fast and the other one will be slow.
Like overtones of some sort. That's really interesting.
Yes, well, it's like the Compton wavelength, but then the Compton wavelength. One of them is the Compton wavelength, but then increased by the relativistic factor, and the other one's the de Broglie wavelength. And the best exposition of this is Martin van der Mark's 2016 paper at the SPI conference. If you want to look it up, you can give a reference for that. He worked this out very nicely.
So is the incompatibility of quantum with relativity more pointing towards gravitational problems, the inability to express gravity at the quantum level? Is that why people are left with this picture of incompatibility?
No, I think it's just that people want to do something that sounds sexy and sounds interesting. This conflict between relativity and quantum mechanics is kind of seen to be a sort of a sexy area of research. It should not be seen as such, because the very origin of quantum mechanics is relativistic considerations. But no, it's not. No, it's nothing to do with gravity. That's another set of problems, which are also an interesting set of problems. But no, I think that's another set of problems.
But so, if the origin of quantum is relativistic in nature, how is it that it's purported to be a conflict?
Because people have developed these two people called Alice and Bob. So you have this idea about quantum entanglement, and it's thought to be extremely mysterious. But I think that if you look at the thing for photons, looking at the entanglement for photons, then there's a big mistake which is always made and it's really pretty much in the first couple of lines of any one of these arguments. It says that if something happens, there's an entanglement, and the two entangled photons fly apart and do something, and if Alice is sitting in the line of one of these things and she changes her polarizer, then that changes the polarization automatically of the other photon, which is outside the light cone of that change that Alice has made. That's the kind of argument that is made. Mm-hmm. Now, that would be great, except the fact that Alice can make that change is not physical. And the reason it's not physical is if I have a photon emission here, bridge of my glasses, and I have a photon runs off from that and gets absorbed here, and the other photon runs off and gets absorbed there, if I take that time and space in the frame of the two photons, then the emission and absorption of this photon are at the same point in space-time, and the emission and absorption of this photon are at the same point in space-time, in the frames of those two photons, which means, or equivalently, I could say that my glasses are contracted down at the relativistic speed to absolutely nothing at all. There is no space and time in between in which Alice could possibly change the polarizer.
Unpack that a little bit.
Okay. Right. The thing is that if you have light, so light is emitted and absorbed. It's an event. So that event So the kind of events we're looking at, if I look at this candle, so light's coming to my eye from this candle, then there's a connect. Then what's happening is that electrons can't emit light; they have to be part of a system. But the atoms here are part of a system; they're emitting light. That light is emitted and absorbed, and then I've got it roughly a foot from my eye. About a nanosecond later, it's absorbed by my eye. Nanoseconds nothing these days. We can measure sub-nanoseconds. So we can do time measurements faster than that. So the light takes a nanosecond to go from the candle to my eye. Or if I'm looking at, I can't follow stars.
I love that you have a candle just on your desk here. This is, people who are just listening, this is old-fashioned lighting system. I've never seen this.
I'm afraid the lighting on my face is coming from a pressured halogen bulb over there. So that's yeah.
But still,
it'd just be black in here, unfortunately. But yeah, it's lovely. A bit of fire. So that's a light nanosecond. But if I look at one of the stars up here, that's 4 light years away. However, relativity is quite simple. If you go faster and faster, things get closer and closer together. You get this relativistic contraction. At light speed, that emission and that absorption at light speed takes place for the photon traveling from the candle to my eye. Both the candle and my eye are at the same point in space-time. Emission is contracted by relativity down to nothing at all.
It almost sounds like they're connected to one another to me. Like
they are.
Something that had extraordinary stiffness, which was connected, would be experienced by both the sender and the receiver, essentially instantaneously.
This is what Carver Mead was saying as well. Look, if you look at a star far away, the same thing. That distance, your eye is on the star, and the star is in your eye, quite literally.
Yeah,
because for the photon, they're both at the same point in space-time. Now, likewise, any experiment that any Alices and Bobs and Teds and anybody else can do, those photons feel a transactional relationship between the emission and absorption, where that transaction is a light speed transaction. It happens at the same point in space-time. If Alice is fiddling around or Bob is fiddling with any polarizers, the light knows about that because everything is instantaneous for the whole quantum system.
Yeah, its configuration will be reflected at either end of the chain.
That's right. So the thing is a quantum interference over the whole length of that interference, and that can be light years away.
But light speed isn't instantaneous, right? So help me connect the fact that there's a speed limit to light and the instantaneousness of this change.
This is a very good one. You see, the thing is, light speed is both instantaneous and 2.9979 times 10 to the 8 meters per second. How can it be both? Well, the thing is that what we're doing is we're dividing. What is velocity? Velocity is a division of space by time. You're dividing space by time. Okay, so you're doing a division of space by time. So velocity isn't what you think it is. It's not a vector. Velocity is not a vector because a vector has the property that if you add a vector to another vector, you get in this direction, you get a vector that's twice as long. You go the other way, you get a vector of 0. Velocities don't add vectorially. If you're traveling at 0.99 c and you fire off a bullet at 0.99 c, it doesn't go at 1.98 c, it goes at 0.999 c. So velocities are not vectors. So velocity isn't what you think it is, and distance and time are not what you think they are in terms of the collective, in terms of the common view of what space and time are. If you're sitting, okay, so imagine you accelerate in a rocket and you're going 0.99 the speed of light, and you've been accelerating for a long time. You'll have felt that. That's a lot of G's for quite a long time. You think, right now we're really traveling 0.99 c. Then imagine you do it again, and you do the same burn, and you feel the same G's. So okay, you do that, and let's imagine you're doing 0.99 c. So it's going to take you a certain time to get to Alpha Centauri. You're going to Alpha Centauri. So let's say it's going to take you 2 weeks to get to Alpha Centauri at this speed. It's going to take you, in your frame, it's going to take you 2 weeks. I've not done the exact maths. Okay, it's going to take 4 years, traveling at almost the speed of light for any outside observer. But in your frame, because time's been contracted, it's only going to take you a couple of weeks for you. Now what you do is you sit there and you do another burn, the same again. So that other burn takes you up to from 0.99C to 0.995C or something. Not much gain from the outside world. It's still going to take you from the outside world 4 years. But now it's only going to take you a week to get there. You will get there twice as quickly in your frame. Work it out.
Can I take a crack at this materially? I mean, the way that I look at it is that the configuration of the system is reflected at both ends, the receiver and the observer, which makes it appear that any changes to the configuration are instantaneous from a material perspective. But the actual photon event is a deformation event materially that requires time to transpire. So the photon as an event has some time length to it, which is characteristic of the speed of light. But the configuration is instantly available. If you know what something looks like here, then you know how it's configured at the other end because they're materially linked to one another. I don't know. That's my interpretation of this kind of data.
I think the way I look at it is I think you need to look at 3 frames. You look at the emitter frame, the absorber frame, and the photon frame. But the photon frame is always, emission absorption is always at the same point in space-time relativistically.
Right.
So
because both atoms are participating in this event simultaneously.
Both of them, you've transferred a unit of energy from the emitter to the absorber. So both of them are involved. One's lost a unit of energy, the other one's gained that unit of energy. Energy is conserved in this way. But it's only conserved if you look at it, but you have to look at the whole system. And the thing is that people have taken on board in the field this criticism that for photons, really it's not physical to get in between them. But people have then looked at stuff using electrons, which are obviously not photons, and looking at quantum systems. But they actually have, although the argument is then more difficult, to set up a quantum system, you really need to have what quantize means. It means you put it in a box, or you put it in a bowl, or you've trapped it inside some system. So if you set up a quantum system, then that quantum system is subject to the harmony of phases. Read De Broglie's thesis. So you have these 2 sets of phases running through, group velocity and phase velocity, running through one another in such a way that Vg times Vc is c squared. This is in any relativistic quantum mechanics textbook, one of these. So people should know about this kind of thing. So Vg times Vc is c squared. And you have to consider both phases, the fast phase and the slow phase, for a transaction. And exactly the same thing happens. You cannot have a quantum system which doesn't know about the whole system, because if it doesn't know about the whole system, it's not in the system. The system is like bookends, the boundaries of the whole system. So the argument holds both for photons and for any other particle, any other relativistic particle. The only reason people think there's a problem is because the theory to which it's compared is not relativistic quantum mechanics, it's ordinary quantum mechanics, and then it looks like there's a contradiction between the two. And there is, because things are everything's relativistic.
It speaks to me of a deeply interconnected system of stuff, of this fundamental fiber of existence, which is very much sewn together amongst all of these isolated actors. And when we treat them in isolation, things get really confusing. But when we consider the network architecture as a whole, it starts to make a lot more sense.
That's right. And if you think about it, your star stuff being powered by starlight, by sunlight, everything that's flowing through us, the whole process which we're using to talk to one another, has come essentially from that lovely star of the sun, our sun sitting up there, powering the food that we eat, and that's powering us. And
when you talk about in the thought experiment of the travel between systems and the apparent change in the time experienced in the moving frame versus the still frame, do you have a physical interpretation of that, or is your sense of time just this?
Yes. Yes, I do have a physical interpretation of that. The way that Einstein originally worked out the equations of relativity was by thinking about light in a box. And if you think about everything being made of essentially relativistic oscillations, which it is, the solutions that Dirac comes up with in the final chapters here, in the electron stuff section, so let's find it. Oh yes, here it is, page 263 of the 4th edition, section 69. There's the solution of an electron motion on that page. Those solutions are light speed oscillations. Everything's oscillating at the speed of light. That's for an electron in the relativistic quantum mechanics, and they're always light speed. So if you have light in a box, then what you want to do is we want to have a look at the relativistic transformations of light in a box. So if you take light in a box, so we move the box, what will happen is light's bouncing backwards and forwards in the box. So if it's moving away from you, the stuff which is moving in the same direction as the things moving away from you will be red-shifted, and the stuff that bounces back and comes back to you is blue-shifted. Now, if you take the baseline as being, say, green, and then it's blue coming towards you and red going away from you, then the thing is that there's more extra energy in the blue part, because that goes from 1 to infinity, than there is in the red-shifted part, which goes from 1 to 0. There's as much phase space in those two different things. But and the relativistic factor 1 over the square root of 1 minus v squared over c squared is better expressed in terms of the red shift and blue shift of those two things, because that factor is just 1 over r plus r, half of 1 over r plus r, where r is the red shift. So it's just the properties of what bound light does that are the equations of relativity. So this whole thing about, so coming back to the question you asked earlier, Anastasia, about the speed of light. The thing is, the speed of light is, what's the speed of light? The speed of light is you taking your local ruler and doing dx by dt, and dividing by your local clock. Now that's constant. So if you measure light in the spaceship traveling at 0.99 c, it'll still travel at the speed of light. So that's the constant that you're doing. The thing is that your rulers and clocks are being messed up, because your rulers are shrinking, and they shrink down to nothing at the speed of light. But you don't notice that, because you say, no, my ruler hasn't shrunk. It's still the same size. If I measure myself, if I divide myself into that, I'm still 6 feet tall. So what's happening is the basis on which you're measuring things is changing. And in fact, the speed of light is in some senses infinite. It's infinite because it travels any distance in 0 time in its frame. However, measured in any other frame, it's doing 2.9979 times 10 to the 8 meters per second.
So is this a variable speed of light theory then?
No, it isn't. No, the speed of light is absolutely constant. It's because it's because you're measuring different things. Mm-hmm. You're calling the speed of light local to you is different to the speed of light. The size of your rulers and the rate of your clock and the size of your rulers is different depending on how fast you're moving with respect to somebody else.
Do you have a definition for time?
No, but for frequency, yes.
I see.
I think that Anastasia's question could be framed in terms of what do you imagine the Ur stuff is doing during the activity called a photon?
It's oscillating at a frequency given by E as h nu. And that frequency, think about it, a clock is not a time, a clock is a frequency. Tick tock, tick tock, tick tock. You mustn't try and define time, you need to define frequency because that's your measuring device.
Well, so isn't that a definition for time?
Well, yeah, time is what clocks do, and in this case, the clock is this oscillatory behavior.
No, it's not a definition for time because, first of all, you have to decide what division is.
Well, so if you're measuring something and you're watching it oscillate, there's a zero.
What are we talking about? What is oscillating? This is charge, right? What are we talking about here?
Well, I'm thinking about an atomic clock, right? Where you have the cesium atom that is oscillating at 9 billion cycles a second.
Yes, that's right.
And there's a small size and there's a big size, and the oscillation between those.
Are those spatial oscillations? Those are energy state oscillations, right?
Yeah, but what you're doing is you're measuring a certain number of those and then calling that a second. In fact, that's the definition of a second at the moment.
Right.
That defines the time, but it doesn't say that that's what time is.
I unpack that
because they're indistinguishable in the theory, from what I understand.
The thing is, it's a measurement of time. That's a different thing for it being time. Now, and the difference comes in understanding what division is. Because what is this thing we call division? I mean, you divide 1 divided by 6 is a 6. That's okay. That's okay. If you're dividing a number by another number, you get a rational number. But what happens when you divide something like distance? So you divide something like. So if we look at, okay, well, you're going to get the uncertainty relation coming right at you in a second. You know that, don't you? So the uncertainty relations are things like the energy time uncertainty. You know about this. Delta E delta T is less than or equal to half h bar. Okay. Now, that's much more interesting if you don't use energy, but you use frequency, because energy is h nu. So h nu T is less than or equal to half h bar. Okay. We've got an uncertainty relation. We can't know them both at once. So which one do you want? At the quantum level, you cannot know those both at once. It's an uncertainty relation between frequency and time. So which one do you think is more fundamental? Well, if you think about what time is this floppy thing, which is anything you like, depending on how fast you want to go. So whose time? However, frequency is a measure of energy. And if we take a specific photon, the photon going from candle to eye, then these are yellow photons here. Then I know what the frequency is. I know what the wavelength is. What is it? About 550 nanometers. And I can work out, and I know the frequency of that. I can work out the frequency if I do some sums. What is it? I've forgotten what the frequency of typical photons are. I know their energies. So what's happening there is that the thing that's being transferred from candle to eye is energy. It's a lump of energy's come across. It's a lump of frequency that's being transferred, not a bit of time. It's taken time for that frequency for that stuff to get there. It's taken a nanosecond to get from the candle to my eye, and that can be used as a definition of the space which I'm sitting in. But there's a different definition for space for every observer and a different definition for time for every observer. So time and space is just floppy. But they're floppy according to rules which we can use to work out what other people's time and other people's space will look like. There's a reciprocal stuff between you guys and me, and we were both rotating. So you've got a vector going down here, and I've got a vector going up here due to the rotation of the Earth. We're in different frames. And we therefore have different rulers and different clocks, but we can work out they're pretty closely equal. We're not moving very fast on relativistic scales. But time and space
to me,
huge.
Sorry.
Energy is transferred. Uh-huh.
Yeah, I guess to me it makes sense that a clock that you take under extraordinary inertial pressures is going to suffer from those pressures and slow down inevitably as a result of that inertial strain. In following from Mach's principle that things are connected to one another, it just makes sense to me.
That's true, but that doesn't. So if the inertial frame of the clock is causing it to slow down, then you still are asserting that time is what clocks do.
I mean, they have to be. It's inseparable in terms of the equations.
But I'm not sure that John agrees.
Oh,
I'm not sure I agree either. I think frequency is what clocks do.
Sure.
Clock does frequency. We impose time by saying a certain number of cycles is an amount of time.
Right.
But so why is that not a definition of time? That's the part that I think is the last little like.
It still seems you're defining it by what clocks are doing.
Well, but
am I missing something?
I think you are missing something, because I think that John is saying that frequency is what clocks do, and frequency is one measurement of interval, but that's not what time is.
Let me come back to that. I just need a comfort break. Hang on.
All right, we got a quick bathroom break there. Anastasia will be back in just a second.
That's no problem. Yeah, no, it's a very interesting line of inquiry that we're on here, Michael. And there's a colleague of mine, Garnet Ort, who could perhaps say this better than I can. And there's a talk of his up on Quicycle, thinking about the nature of time, what's happening. But you see, there's a difference between time as an extensive thing and time as an intensive thing. I really need to say this to Anastasia as well, I think. And I think the point is that if something comes, I'll save it.
Yeah, just hold on one second. I want Anastasia to hear this as well. Yeah, the intensive versus extensive properties is a really fascinating subject because there's all sorts of violations of this, especially in astrophysics. Yeah, let's talk about it in just a second. Sorry.
Yeah, no. I find it is absolutely fascinating. The thing is, we tend to think of things and their inverse as kind of being the same thing, but they're not. Frequency is not the same. Energy is not the same as time. And it's because we're used to thinking, I think, of numbers, inverse numbers, as being the same sort of thing. But also they're not. Because there's a difference between counting numbers 1, 2, 3, 4, 5, 6, 7, and their inverses. One sheep, two sheeps, three sheeps, etc., etc. is a different kind of thing to one sheep, half a sheep, a third of a sheep, a quarter of a sheep. Certainly for the sheep. So,
yeah, I think there's something kind of scary about shirking the definitions of fundamental aspects, right? If physics doesn't start on day one of the classroom by working out what the fundamental ideas mean, then it's very difficult for especially young people or people who are new to the field to begin to imagine how to improve our conceptions of these ideas and how to, we have to be on the same page about. But unfortunately, when you walk into Physics 101 at university, everything starts with, okay, time, and this is distance, and blah, 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 but they're not really discussed in terms of initial principles.
I think if I ever get my hands on designing a university course, things will be different for this. I think it's extremely important to get to those fundamental principles, otherwise you don't know what you're talking about.
I think it's really important. I spend a whole lecture in my intro astronomy course just talking about what light is, first of all, since everything we do in astronomy is based on light, and there's no section built into the course for that when I arrived. I was like, hold on, wait a second, we can't go on and talk about analysis of light with at least considering some ideas. We talk about Carver-Mead and...
Well, that's the drawback of not having a physical model for light, because if you don't have one, then you have to have a very mathematical conversation. And yours is a course for students that perhaps aren't the most mathematical inherently. And so it's much easier for last year's professor to gloss over it.
Sure.
And just accept that this is, we deal with light, but don't worry about it because it's too difficult. He has no idea.
Well, you said something really interesting earlier where you were like, the quantum mechanicists view the intermediary transition between the receiver and the emitter as being non-physical. And I think the fact that you say that physics has entertained the idea that something is non-physical is at the crux of the matter. It's very, very strange that someone in physics would be like, well, that's fine, that checks out.
I think it's very, very insidious as well. One doesn't live in the real world, one lives in the world one invents. But if you invent a world in which something happens and then somebody does something and then something else happens, that can be a very persuasive argument, but that can be you have to be careful what's physical and what's not physical.
Yeah, a lot of people accuse me of being a materialist. They're like, what's your problem? You're taking the magic out of the world or something. And I'm like, look, there's all sorts of magical, non-physical things happening in my daily life, my relationships and my motivations, and there's so much magic out there, but it doesn't really belong in physics, right? Physics should be physical. That's what else is going to study the physical world if not physics? And it's just very strange that of all the sciences, the non-physicality would be introduced into physics.
Well, I think that this is at the heart of this discussion that we were having before we took this break, which is the difference between time and the measurement of time. Because time seems unphysical in some way.
Well, it's not that it's unphysical, it is physical. But look, we're dealing with two different things here. I'm going to make a pendulum thing here. The thing is that if I look at, or if any one of us looks at the universe, we are looking at the absolute pinnacle of space and time. And out from here, about this far away, a sphere around my head, is 1 nanosecond ago. Mm-hmm. And the things that are influencing me are on a series of concentric spheres centered on the thing which is me, which are ago and more ago. That star up there, which has now come out, is probably about a 10 or a dozen light years away.
At least.
Ago. So we're looking at things. This is an extensive thing. We're talking about time as an extent, an amount of time, an extensive time. If you're talking about frequency, then something's happening. The thing is coming back to its starting point. It's going round some sort of loop. It's intensive. It's happening at the same place. Tick, 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 always the same place. Whereas the time stuff is going out in ripples as ago, further ago still. So we're talking about two different kinds of things. We're talking about something which is repetitive and which has a frequency associated with it. And that frequency is also, quantum mechanically, its energy is h nu. So that's an intensive thing. But its inverse is something which is extensive, which has an extent. And the same is true for space. If we talk about the frequency, we talk about a frequency in space, that's related to the momentum. So there we have, which is related to the spatial frequency, which is that thing that we're talking about in terms of the oscillations of the wave function, the shape of a wave function when it's trapped in a box. So
but it seems like this is talking about two different kinds of time. One of which is the clock, and the other one is the cause and effect, I guess?
No, we're talking about, yes, it is cause and effect in a sense if we're talking about events. But no, we're talking about a thing and the inverse thing. We're talking about time and inverse.
The reason that I see it as cause and effect is because what you're saying is that there's an oscillation which you can measure locally, which you say is the intrinsic time, the frequency. But then there's this extrinsic property of that oscillation propagating out to other things, and so is almost a memory of the state of the thing that's oscillating, expanding outward as ripples in a pond.
That's right. If you look at it, ripples in a pond is a good analogy. Imagine a pond that's had a stone thrown into it and you freeze time. You look at it, you see a series of oscillations. Those oscillations are measuring distance from the event. Mm-hmm. They're extensive. So the distance from the place where the stone fell is the extensive quantity, which goes smoothly out from the stone's impact all the way out. However, what the oscillation is doing is that's dividing that up into intervals of oscillation. One oscillation, and the next oscillation, so it's R, 2R. Take the first peak to be R, the next one. So take the 0th peak to be, wait until the stone's ripple comes to a maximum where the stone hit. Then, and actually it's even more interesting here, because when you throw a stone into a pond, what happens is the point of impact is, first of all, it's the big oscillation, but then that goes down to almost nothing and the ripples move out, and they have a profile which goes from the point of impact, which goes up and down. And a bit later it's going up and down, spreading out as well. The energy is spreading out as well. The wave packet is spreading out. So you have a ruler, you have an extensive thing, which is the size of the pond, and you have an intensive thing, which is the rate of the oscillation, the spatial oscillation, which is acting like a ruler. It's acting like a series of lengths. So you could say, okay, let's use something shorter. We'll use this adiator. So you have something which is, we've got some numbers on that. So you have this thing measuring first wavelength, second wavelength, third wavelength, and so forth. And to get the distance, you have to divide the number of those peaks you have by one of these, by a ruler. And that gives you a number which tells you how many oscillations you've had. And that's the distance, 6 meters or whatever it is.
But those two properties are connected to each other and yet disconnected. And the way that because when you throw the pond into the water, the thing that informs the ripples as they travel across your ruler is the rate at which that water slaps against itself as the void left by the rock closes. There's a local frequency that is the initial measurement, and then the way that it crosses the distance is informed by the substance that it moves across, and it's the diffusion of the wave packet. And it almost seems like we're talking about they're two different things that are related to one another.
They're related by an inversion. But inversion is not a neutral process. You can invert a number and get another number. When you invert time, you get a frequency. When you invert frequency, you get a time. And they're different things. They're each other's inverse. And that inversion is not when we're dividing something by something else, we're doing something which is representing something physical as well as representing something mathematical. Mm. And we don't realize we're doing that. We do it so automatically, and we think that it's just such an obvious thing, but it's not obvious. The division itself is the act of division, time and 1 over time. You don't have the same units. One's in hertz, and the other one's in meters.
But the thing that is creating what you're measuring is the oscillation at the center.
It is, but that thing's not fixed. If I take my stone and I throw it in higher or faster, then I'll produce ripples which are closer together.
Absolutely. And so and that's, I think, the heart of it, which is that time has to be defined for each reference system based off of how hard you throw the rock, which is what Shiloh was saying about the inertial tendency of clocks to change as you're moving. Because even when we've talked about this before, where it's okay, so you have an atomic clock and you put it in orbit and it speeds up.
Put it in a wobbly orbit, so it's near the Earth sometimes and far away from the Earth.
So the gravitational... Go ahead.
Well, yeah, just to clarify, when it gets closer to a lot of atoms, it slows down. But this actually makes a lot of sense to me in terms of the atoms being under a great amount of pressure all of a sudden because they're pulling on each other.
Well, if inertia is the act of being pulled on by the masses around you, as you're closer to a larger mass, you'll have more of that pull, which is gravitation, which slows the oscillation down. And so is the calculation for the strange behavior of an atomic clock in orbit just a physical result that has to do with separation from the mass?
No, it's not separation from the mass. It's doing work. So imagine you're climbing up a mountain. Imagine it's you who's the clock, and you're climbing up to get into higher orbit by climbing a mountain. By climbing that mountain, you're doing work. You can feel it in your legs. You're pushing up to get up the mountain. Every single clock in your body, every single oscillator in your body is speeding up because you're doing work on it. You're putting energy into it. More energy, H nu, here's H nu. So, and then when it comes down in the gravitational potential, it slows down. You get the energy back by sliding back down the mountain on your skis or whatever. So all of the analogies, your one, Michael's one, and the one I've said, they're all connected. They're all true.
Mm.
So,
can you? How did the intensive versus extensive properties play into this?
Well,
I missed
that. The thing is, thinking about time relativistically, you're imagining going around a loop in order to have an oscillation. You have to first imagine you have a light clock. So you have something which is a box with light in, going tick tock, tick tock, tick tock with light.
Sure.
What's happening is that light's traveling backwards and forwards, but when it comes back to the same place at the same point, you've been around a loop. You've been around a loop of space and time. There's been some time has elapsed and some space has been covered. So you've had that loop. Make the box bigger, it ticks more slowly. So you can work out what your light clock rate is by the rate of ticking. But you could also do it by measuring the frequency of the light. you could use the frequency of light as a reference. That's a different clock. And what's happening to the frequency of that stuff is as it goes away, well, you don't see it. It's out of your light. It's out of your... You only see it when it comes back. And you actually only see it when it hits you.
So you're saying that light can be described both intensively and extensively?
Yes, you're doing both of them.
I see.
The extent that it's had is stuff that's been away from you. It's out of your... If light is emitted from, and you're emitting light at 300 Kelvin, that stuff is gone for you. It's outside your light cone straight away, never to come back. But if it does come back, then it's been on a journey, and that journey has been extensive, and it's that you then say is the time, or the space equivalently, space and time being equivalent here. So it's the extent of the size of the object which you're making to oscillate. Of course, we can talk about cesium atoms. We can talk about a what do you call it? A
pendulum.
A pendulum. Yes, a clockwork clock, where the excursion is over a second, roughly, or half a second, or whatever it is for the pendulum.
Interesting.
But the thing is, inversion is not a neutral process. It's not a process that gives you the same thing that you had before, except the numbers, same sort of thing. Only for dimensionless things is it. For anything else, it really changes the units. It changes the nature of the object. An inverse time is frequency, and inverse frequency is a time. Inverse time is a frequency, and inverse frequency is a time. So that it's not that time is frequency, not at all. They are certainly related. Obviously, they're related by inversion. But if you want to say which one's fundamental, the only one that has content is the frequency one. There has to be some energy. There's no energy if zero frequency, you've nothing to measure.
And frequency is the intensive property?
Frequency is intensive and time is extensive. Momentum is intensive and space is extensive. Delta P, delta X, less than or equal to half h bar. Also an uncertainty relation. And the reason is that, well, the uncertainty relation, I taught in an electronic engineering department for 30 years. It's just a property of a Fourier transform. It's just a property of an obvious property of frequency. If you know exactly what the frequency is, then you have to have an infinitely long wave train. So, and vice versa. If you know exactly what the time is, then you've got a delta function, and you don't know the frequency at all. So the two things are not both knowable at the same. I'm going to say at the same time. I'm sorry.
in the same maybe in the same measurement.
Yes, in the same measurement, you can know one or the other. But the one that has content is the energy one. And it's
interesting. Our friend Steve, who's been on the podcast, has made something of a career out of finding contradictions in the application of intensive versus extensive properties to black holes. And a lot of his argument is based on the idea that parameters can't flip-flop. Some things have to be fixed. And so the idea that something could be described both intensively, the same phenomena could be described both ways, is a really fascinating idea.
But what I'm trying to say is that it's not entirely the same phenomenon that you're looking at, because the intensive property has to be local and the extensive property is delocalized. Because the way that we're talking about this is that the extensive property includes distance traveled.
Yes, includes an excursion. Yes.
And so it's not the same thing, because what you're doing is you are adding something to it in order to be able to evaluate it. You're basically saying that in order to track this intensive property extensively, we have to move across some distance to see what it's doing.
That's right. But remember, the kind of clock that I have here is going to influence what that distance is. So you can have a light clock, but you can have a pendulum clock. One's much faster than the other, obviously. Mm. So, and they're also subject to the relativistic transformations, which one needs to take into account as well. So yeah, I mean, they are related, and we do use clocks, and we do have a definition for the second, which is some number of oscillations of the cesium atom in a cesium clock that's at a particular, elevation in a gravitational potential well. So that will make a difference.
But so why, I mean, you hear so many people who are using and abusing the nature of time and how spooky and how difficult and how strange it is to say kind of wild things, whether that's
time travel.
Time travel and all these kinds of things where you hear people abusing the mysteriousness of time to justify odd things. Do you think that that's...
Yes, they do. You're absolutely right. But I think to look for where the flaw in the argument lies, it's good to look at the point where they set up the problem. It's always in the point where they're saying, where you're telling yourself a story as to what's going on. That's where the problem lies. And then things follow from that story you've made up yourself. But if the story you've made up yourself is not physical, then it's just not going to happen. So you've got to make sure that at least it's going to be physical.
And so time is inherently physical, and it is. There's two components of it. One is the origin point. The other is the experience. Is the I want to say the experience.
I'm still not going to say that time itself is a physical thing, because time has no content. Whereas frequency does have an energy content.
Well, can't time just be a measurement?
Yes, and one can measure time, and one can use a frequency to measure time, certainly. But that doesn't make time have content.
I mean, I guess the argument is that time being a measurement of motion, whereas frequency contains some momentum to it. There's some energy to it, right? So it's some material in motion.
Well, it's like a second order examination of it, right? Because you're looking at an object that is doing something, and that is frequency, but time is above that, where you're saying you're measuring what the object is doing over a set number of iterations.
I think there's something here that perhaps if we go to the maths might make things clearer. If you look at the dynamics of this, we're talking about d by dt and d by dx of something. There's been some change in something. But d by dt and d by dx is really a division by a little bit of time. D by dt is 1 over a small amount of time. What can be thought about as being 1 over a small amount of time? That's frequency. So your differential itself is a frequency. So when you're describing the dynamics of something changing, which is all you're ever going to experience, then it's always coming in the inverse. You don't experience time directly. You could measure it, how much time has elapsed, by saying, I'm going to take this frequency standard and count a certain number of oscillations. Certainly you can measure it. But that time, so you measure some time, but what does that mean? I mean, as you've measured the time, your time has moved forward. And the time... Now I'm not sure I'm saying something correctly. Hang on.
I think that... so I'm following what you're saying, which is... What you're saying is that any time that you're attempting to measure d over dt, you're getting a frequency, right? So a year is the amount of time that it takes the Earth to travel the distance around the sun.
Right.
But in the process of measuring that rate, you've...
Oh, yes. It's a nasty one, isn't it? Because...
It's so hard to use the right words and to not use circular definitions.
Yeah, not to use time at the same time. Yeah, I know. No.
Well, I think that what it is that because nothing is stable, the amount of time that it's taken for the Earth to go around the sun, the whole system has also moved, and so the frame has moved in a larger box, so to speak. And so, in order for you to be able to say that time has passed, while you've done the measurement of the Earth going around the sun, you have to have the sense of a larger motion, that motion is contained within.
That's right. I mean, we can measure time and space. What I'm saying is that the physicality of existence doesn't lie in time or space. It lies in inverse time and inverse space.
The relation.
The material.
The material existence of objects that one can measure.
But that's the relation between the objects.
One is a static concept, one is the dynamic concept.
So a relation between objects is a dynamic concept.
They're motions.
Yeah, exactly.
In particular.
Exactly, yeah.
That's in frequency. That's in the frequency domains. So
I mean, fundamentally, time is just a comparison of motions to one another. You have a standard motion, and you're comparing your new motion to it. It is an abstraction.
To measure my height, I divide the ruler. I see how many times the ruler fits into my height. I'm doing a division. So, and that process gives me a number, not a length. So I am whatever it is. What am I of these? I'm 12 of these things long. So, but you're dividing me by the ruler to get that height, and you're doing the same thing with time. You're dividing the frequency. You're dividing. You're doing a division in terms of measuring.
It's a comparison, right? It's a comparison.
And that comparison gives you a number, and that tells you how much of something you've got.
Mm-hmm. Yeah.
Whereas the amount of stuff which exists is something which exists in the frequency domain. Mm-hmm. So the atoms and electrons and protons and neutrons of your existence have that existence due to their oscillation.
Which says to me that existence is best conceived of as on two levels. One is the material substance, the ur stuff, the fiber of existence, as I like to call it, the stuff. And then you have various motions of that stuff which account for what we would consider these particles, right? They're just essentially different conformations, different dynamic conformations of that stuff.
That brings us very nicely back to what the electron is and why it gets big and small. I think what the electron really is it's a configuration. It's a topological shape of this stuff.
100%, yeah. It's so fascinating how I don't know, we have conversations with people about these kind of things all the time, and I feel like everybody is on the edge of gripping this, but the fact of these terrible failed experiments to detect the ether seems to have excluded the possibility that this is even a solvable problem to most people.
Yes. Now, actually, I had something here that I meant to... I managed to lose it. Doesn't matter. I have a piece of paper with things I wanted to remember to talk about.
Yeah, take your time.
Typical. Never mind.
Well, I guess just for people who are listening, if you're not familiar with the ether experiments, people were essentially assuming that there was a substance which was separate from matter that they could detect, right? Because there would be drag available as the real matter moved through it. And the new conception that a number of people are converging on, which is essentially what we're talking around here, is that actually that stuff is the same stuff that makes up the matter that we're aware of. And so it's essentially indistinct. You can't actually separate it out and pull some observation of that's separate from your matter, because it is the same stuff that makes up the matter.
Which to me feels like what quantum field theory is saying fundamentally.
Yes, I think this, if it's not saying it, it should be saying it.
It's just speaking a language people aren't familiar with. I think it is saying it, but I don't think that the translation has been adapted properly.
Yes, I think that's... I think we're all struggling with I always say, sort of got your fingertips on this stuff, but haven't really got a full picture of it, because it is very difficult to say that things happen at the same time when you're talking about time, because you're using the word in two different senses, and you're struggling around like something trapped in 2D that's trying to understand something which is 3D. And I think what you're saying, Michael, just now is absolutely right. Because we're trying to measure the stuff of existence with being part of the stuff of existence, with the floppiness, with the tools that we have at hand, which are rulers and clocks, which themselves move with gravitation and with acceleration, make it very, very difficult to grasp what's going on in a bigger picture. And maybe it's in fact inherently ungraspable.
Well, to grasp something fully, you have to be able to stand somewhere and watch it from the outside.
Yes, and that's right. And I think we can't. There are certain parts that we can't get outside of. We know the dimensionality that we're living in, but we don't know what's causing that dimensionality. So, getting the cause of something may be difficult.
And our best bet would be to model it, right? Because it's not a system that's empirically touchable. Like, you're not going to be able to touch the fiber of existence because whatever you have is made out of that same fiber as well. And so the best bet is to come up with models for what it could be, but they're irreducibly hypothetical, it seems like, at some point, because you'll never be able to touch them.
Yes, because what you're trying to touch is what you yourself are made of. So, yes. Yep, but I think we're doing pretty well in terms of getting stuff which does a pretty good description of reality, and we can do quite a lot with it. So even though there may be things that are ultimately unknowable, it doesn't mean that there's not still a lot of work to be done in understanding what we can grasp.
So something that I wanted to ask you about was the technological implications of this, because you come from a technological background.
Ooh. Oh, crikey Moses, Michty me. Can I say
Never heard that one.
Yes, no, it's a bit Scots. So, well, what are the technological implications? Well, I think there are many and various, and Quicycle is working on a bunch of these. So we have a set of projects which are ongoing. I think I don't know how much I can say.
That's so frustrating. Anytime that anybody's working on anything technological, they always come up against the edge of it, and they say that there's only so much that they can say.
Well, the thing is that I can say one or two things. Look, I think what the new theory does, the new theory, dg equals 0, it's an advance of relativistic quantum mechanics and electromagnetism. What it does, it allows you to think things you otherwise couldn't think about at all. Now, when I was designing this thing, single electron transistor, I was thinking quantum mechanically in terms of quantum mechanics. Now, compared to quantum mechanics, if you take quantum mechanics as being a bicycle, the new theory is a supercharged vehicle that's capable of traveling through several different dimensions. It's a much, much more powerful tool for thinking about things. So does that have technological consequences? Well, yes, of course it does. Now, there are several things. One of them has been a warning. The Sapphire people are producing interesting stuff at the moment. I don't know if you know that project.
We've tried.
Yeah, go ahead.
Yeah.
We've tried. But again, the one person we got from the Sapphire project to come on the show couldn't really tell us what was happening. It was one of those things. And I don't think they've I don't know, last time I checked, they hadn't put out any updates in a few years.
No, that's right. But I phoned them up, I talked to them and warned them of some of the things they might be doing because it could kill them.
Oh, no.
No, that's one of the things that the new theory can do. It could, if they're doing what I think might be doing, it can be extremely dangerous.
Okay, break that down for us.
Well, shall I break it down or shall I not? I mean,
you could break it down by analogy if you don't want to give away the technical secrets.
I mean, look, the thing about the technical secrets and not giving away the technical secrets, there is such a narrow window of people that would be able to do anything with those technical secrets.
There is, but the question is, if you want to produce something which Sapphire people are doing, I think, which is going to produce huge amounts of energy at very low cost, then you'd really rather that was done by people who you would trust to do that kind of thing. So you'd rather it was done by the good guys, as it were. So perhaps you don't give too much away in terms of exactly how to do stuff. But there are lots of areas. Arnie and I, if you look on our website,
Well, hold on. Let's not leave the sapphire thing. Let's see if you can talk about it in a way that is sufficiently abstract that you're not giving anything concrete away. Because everyone, myself included, everybody wants to know.
It makes it really hard otherwise to have any enthusiasm for the project if it's just somebody saying that it's cool and you don't.
We're going to do amazing things, and then you're like, well, what kinds of amazing things? And you're like, well, we can't talk about it.
Okay, I'll tell you the sort of amazing things that I think we can do. I think we can devise a system which can cool the planet. So I think we can devise something which is strong enough, powerful enough, that we could choose any kind of global cooling that we wanted.
Free AC for everyone.
Yeah. Global air conditioning. So I think
so you're talking about like a planetary scale system. Not ACs in every house, but one AC for the planet.
Kind of, yes. Although you'd have to be quite careful where you put it. let me. So perhaps you'd want to do quite a lot of small ones because that would just be an awful lot safer. Let me give you an analogy. Remember Marie Curie? She was doing fantastic work on radiation, which killed her. And I think that's the kind of thing. The sort of thing is that you can get into new areas of technology, and those new areas of technology have good sides to them, very good sides, but they also have dangerous sides. If one's playing with an awful lot of power, one really needs to be careful which way you're directing it. You don't want to point the gun at yourself. And I think the Sapphire people are in danger of doing that in some respects, which is why I put out the warning to them.
Yeah, I went down the rabbit hole one time of investigating the different Los Alamos accidents, and they were just doing these ridiculous experiments at some point where they had like a ball of plutonium with like a little shield over it, and they would, as long as like the shield was cracked, it wouldn't go into a chain reaction, but they'd just stick a pencil in there, I guess, to hold it up at some point. And they lost like several dudes doing this experiment. Like it went blue flash, and that was it for that person before they finally decided to put some controls in place, I guess, that were more, robotic or something.
Well, we've been designing a new energy source based on the new theory that's more potent than fusion, than a fusion reactor. But I did some calculations last month. We were developing a prototype for this thing inside the group. But I did some calculations, and I realized the thing was so powerful that it really risked, risked destroying the planet.
Oh, no.
If it ran away. So put a stop to that while we think about the controls that we need to put onto it in order to make sure that things like little accidents like that don't just happen. So
this is why people are terrified of scientists. These things make the headlines.
Anyway, so
do you worry that by being secretive about the technologies, obviously there's one arm of this which is safety and making sure that the planet doesn't get destroyed, but do you worry that you would prevent there from being a critical mass of people working on it? Because, the Quicyclists, which we still haven't unpacked why it's a quantum bicycle, we'll get there later, but the Quicyclists are, you're not the world's largest group. You're not funded like CERN. I don't know that you have, a Department of Energy or a DARPA grant, and so do you worry that the advances that you make will disappear without a larger network of people working on them?
I do, and I've tried to take some steps to do that. There's some very smart, although we're a small group, there's some quite smart people in Quicycle. So what I've tried to do is to make sure that Quicyclists at least understand the principles of being able to do this this stuff. And we do talk about this, of course, and how to bring these things out. But there are many. The thing about a new thing, you see. This is a perennial question, of course. We have a new theory. What can you do with it? Well, of course, you don't know what you can do with it, so we start doing things. So the thing that we're trying to do is to start by putting together different consortia to engineer different kinds of things that otherwise... The new theory allows you to think about things that you couldn't otherwise think about at all. So the question is to go into this is why I wanted the Carbamide questions. And they were fascinating, by the way. That's really worth looking at some other time. But the reason it wasn't what I was expecting at all. There's some good ones there, but that was an interesting set of things. So really going to questions as to what where are problems? Where can we make a real difference to new kinds of materials, new kinds of devices, new kinds of systems that have not been engineered before. So our policy has been, I thought, well, okay, we could write a patent about this new thing. But the second you write a patent, everybody knows about it. These things are not secret. They're completely open to everybody. So we decided, no, that's not a good way to do it. What we need to do is just build one. So we started building one, but then, as I say, I did some calculations just on the power output of this thing, and it was it was cosmological. So that this is a dangerous kind of thing to turn on if you don't have it under control.
But this was also when CERN, when the Large Hadron Collider was getting turned on at CERN, there was also the concern that it was going to produce cosmological levels of.
Yeah, that it might produce a black hole. Yeah, I remember that one as well. And no, that's right. And perhaps this thing will be self-correcting, because as soon as it starts trying to create a large amount of energy, of course, what happens is it just explodes, and you end up with hopefully you're far enough away when that happens that it doesn't never gets to that, and that's the likely scenario actually as well. So, but it does mean that one has to think about ways. It's the energy handling here that's a problem.
Because I mean, like when Tesla was working on his inventions, they died with Tesla.
They did, and there's some interesting ones there, and I think I know what Tesla. Oh, that's right, yes. And I think I know what Tesla was. Tesla said some pretty cryptic things, which I think I now know why he was saying them, at least some of them. So yes, they did. And Tesla was a different class of smartness. And yes, things did die with Tesla. That's unfortunate.
Well, he kept his ideas very close to the chest.
Yeah.
And it's not clear how much of his original work remains even. I know like there's some cryptic stories about the FBI carting off all of these, volumes of his work at the time of his death. Obviously his laboratory burned to the ground, and I don't know, there's some strange things revolving around that dude.
There is, but Quicycle is designed. Quicycle Limited is designed to be a non-profit organization whose our main aim is the advancement of science. The idea is to give that job offer, which I had from Philips, do what you want to with unlimited funds, to as many people as possible, to as many people who can really make a difference as possible. So that's what we aim to do. We aim to employ people, like you guys, people who think, people who do, who can make a difference, and then not educate them, but have us educate one another.
Mm.
I think one of the things that we do that I'm very, very pleased about is we have a group of people in Holland as well, a club that I've belonged to for 30 years. We are kind of fanatical about physics, and they call themselves the Fanaten. And the way the club works is that one of us will give a talk, one of us will arrange to give a talk, another person will host that talk and provide refreshments, and we'll do something like what we're doing at the moment. We'll talk I'll talk, or one of us will talk for 2 hours or so, and then the discussion will follow from that, and that will go on for another couple of hours. And we used to meet once every 3 weeks. It has run down a little bit since then, but we meet regularly as well. We still meet fairly regularly. And the club is still going after all these years. I think that sort of thing, where each one of us we just talk about something we find interesting and explain how it works. And then we educate one another in that way. I want Quicycle to work like that too. But you did ask what the quantum bicycle was.
Mm.
Shall I try and say?
Yes, please. That would be.
Have we still time? Well, what the quantum bicycle is it is this motion. It's this double loop motion that I talked about last time. It's the idea is of what is the motion of a piece of Bohr stuff, what's the motion of an electron in space, a free electron in space? How does it move? Well, in a sense, it doesn't move at all. It's stationary. So it's stationary and it's rotating. It's dynamical. So the electron is clearly dynamical. It's got spin, so it has to be dynamical. It has to be rotating about its own center of momentum. But the question is, what's rotating and what's it rotating in? Well, what it's rotating in is it's rotating in this electromass magnetic set of equations of motion, which I've developed with Martin. And so what does that look like? Well, it's a four-dimensional motion. So what it looks like is it looks like wheels within wheels within wheels. It looks like a multiple set of nested rotations. So the analogy that we came up with right at the beginning of this was the idea of a bicycle in space. So you put a bicycle in space, and start pedaling. What will happen is the wheels start spinning and you will anti-spin to conserve momentum. You'll spin in the opposite direction. Now, the question was, what happens if there's spin going on in different directions? So what you can do is you can imagine a bicycle that's got the rear wheel in the normal place, but then it's got the front wheel at right angles to that. And then you start pedaling and you pedal both the front and the rear wheel. What will happen then? We have an angular momentum about the z-axis and you have an angular momentum about the y-axis. And what will happen is you'll tumble round and round over yourself, because to conserve angular momentum, you'll add those two spin angular momenta and get a third angular momentum, which is 45 degrees to both their equal masses. And if you're a massless cyclist, then you'll tumble at some 45 degree angle. Then we thought, okay, well, 2 dimensions, why not go to 3 dimensions? We'll mount 3 wheels, one axis on X, one axis on Y, one axis on Z. And we'll see what happens when we cycle with those, and you get a more complicated tumbling motion. Still, the 3 spins simply add up. But now what happens if we allow the spinners to spin around each other? And we make those spins happen at different kind of rates. So you make the front wheel spin around the rear wheel at half the rate at which the rear wheel is spinning, for example. Then what kind of motion will you get for that? Well, you're beginning to get to the complexity of what the quantum bicycle is doing, because what you have there, or what we have in my model of the electron, is you have a photon, which is already like something which is spinning around its own axis as it moves along. It carries angular momentum of h bar, so something spinning in a circularly polarized photon. And what happens if you take that spinning photon and then make it spin around something, so it spins around an axis? And then what happens if that spinning thing spinning around an axis is itself spun around a third axis? Well, that's the quantum bicycle motion. And what it looks like is, if you project it, it looks like a torus enfolding itself continuously. So you can do this because you can do this with a computer program. So you can make that spin happen, and it looks like a self-enfolding sphere. And that's the quantum bicycle motion. That's the motion of a the simplest stable particle, the electron.
Yeah. It's so funny. I know we probably mentioned this before, but we independently arrived at the same conclusion and made some animations of this.
I saw the animations, and I think they're just, they look like our animations.
That's so cool when people arrive at the same conclusions and don't even know about each other. It's just so, just really makes you feel like you're onto something. It's really wonderful.
So the reason we call it quantum is, of course, because that's the oscillation. That's the wave function of an electron sitting out there in space. That's the quantized electron. And the thing is that it gives you the electron charge and it gives you the electron spin. You can calculate both of them. We did this back in 1987. So
I really, the relationship between spin and charge is something that's still perplexing to me a little bit, because it's funny, if you go to a stock exchange or something and you say, what's the relationship between spin and charge? They'll all be like, there's no relationship between spin and charge. But if you look at the periodic table of the elements, it's quite obvious when you start imagining the way that things actually are found or stable in nature, that unpaired electrons always seem to pick up charge, right? There's clearly a relationship there in terms of the phenomena.
Yeah. You get situations like sodium chloride. I mean, sodium chloride, it so wants to lose an electron or gain an electron. Electronegativity is a name given to this, but why? Why do they want to be so much in what does want mean? Want's really a force, isn't it? What is the force of want in chemistry? Well, that's what we're doing, and that's what Arnie will probably talk about as well when he comes to do the DemystifySci podcast. Yeah. Because that's what he and I have been working on over the last year or two. So, and
I'm really, really excited to learn more, especially because we're moving towards modeling the nucleus as well in this model, and I think you guys have some really cool ideas about the shape of the nucleus as well that I want to adopt. We actually have just started collaborating, fingers crossed, with an animator as well, who hopefully can take these things to the next level. So everybody can look forward to that. But I think we'll eventually be able to model all of the other pieces of the atom, not just the electron.
I should look forward to that as well. The person who could talk more about that in our group is Viv Robinson, who's been looking at nuclear models himself.
Oh, cool. Yeah, we need to connect.
Yeah. I mean, I think that this might be as good a place as any to put a pin in it for at least a moment. We've taken quite a bit of your time, and I know it's late over there.
It's a pleasure talking to you both. But this one's been a bit strange. We talked to you did say that you wanted to talk more about the backstory and so forth. I think we've done that today, at least a little bit.
Mm-hmm.
Yeah, that your story is fascinating, especially because
we never went back to Martin, though. We missed that chunk of about I think you said it was 20 years between Phillips.
30 years. Yeah, no, Martin. Yeah, we didn't get Martin. We didn't get to Martin. We can do that. Well, do you want to do another one tomorrow?
Is that the last opportunity that you have to do it?
Well, probably not, but I'm going for an operation next Wednesday.
Okay. Could you do it on Sunday?
Could I do it on Sunday? Have you at the same time? No.
Well, we could find a time, perhaps. We have one meeting at noon our time.
So we could do it earlier. If we started an hour earlier.
Sunday's going to be difficult to me because my oldest friend has invited us for my mother as well. So I'll be traveling across country most of the day.
Okay. Let's see what we have, because the reason that we're pausing is because Saturdays are
your free.
They're our free day, but because Shyla's been teaching this semester and our schedule's a little racked up, we've been letting people book on Saturdays, but it's been now a month where we haven't taken a single day off. And
we need to get out in the woods really badly.
We keep having these piecemeal days where we'll drive out for an hour or two to sit by the river. But
time. Completely. What about Monday or Tuesday?
Yeah, Monday we could do it.
Monday 6 my time.
Yeah. We don't have anything on Monday. Can you break that time off from lecture preparation?
Yeah, I'll just get up early.
Okay. Yeah. Okay. Well, so then let's plan for your.
Is that the same time as this one for you?
Yeah. Okay. Is that okay for you guys?
Yeah, that's fantastic. Fine. That would be much better than Saturday.
Yeah,
excellent.
Thank you for accommodating.
No, that's no problem. No, just have a fantastic time. Get out there.
Thank you. Yeah, we'll make a new invite and send it to you so you can have it on your calendar.
Yes. And
with a new link and everything.
But do you have some closing thoughts that you could put, a bow on what we've talked about so far?
I think that, whether my theory is right or not, I think that everybody has to really start looking at what the elementary particles are, so-called elementary particles. They're not elementary. They're not elementary at all. And having a model where you've got dozens of these things is just not good enough. We've got to do better than this. and really we can do better than this. And really, the shout to all the young people out there is there's a huge amount to do here in understanding how chemistry and physics and science as a whole fits together, and we need better theories for that than the ones that we're currently wasting a lot of time on.
100%, yeah. That is,
and it has to be science. It has to be stuff that's testable. It has to be stuff that's. It should really be simple. It should really be a simple thing. Stuff cannot be as complicated as at the moment it is. It has to become something which is much, much simpler. Oh, I remember one of the things, that thing I wanted to say as a closing remark. Martin and I used to say that when we're talking about other people and where they took a step off and that messed things up for them later, we'd say this in Dutch, and we'd say that this is something where mensen gaan de mist in, go into the mist. And our mist was MYST as well. I have to say that this is trying to point out where those places where people went into the mist and messed up, I think is something else that should be a series on your Demystify Science. Where did Dirac go wrong? Where did hydrogen physics go wrong? I think.
Where did the mist arrive? When did the mist arrive? This is something we've been talking about doing a piece on.
So we're writing a book right now, and the working title is "Learn to See in the Dark," which is we're explaining the idea that science somewhere went off the rails, and if we continue along the paradigms that are central in many of these fields, we'll never be able to get to the next step. And obviously, the first book is sort of a general overview, because if it wasn't, it would be 1,000 pages long. And so we're trying to condense it down to many different fields, atomics, geology, planetary sciences, consciousness, and be able to give a gloss of all of the different ways that these things need to change. But we look at it as the starting point for a deeper project, which is that we go and we look specifically, okay, how did physics go into the mist? What are the primary documents? What are the letters that these people were sending to each other? And what were they saying in the letters? What were they arguing about at their conferences? How can you trace that descent into madness using their own words and their own examples in order to be able to reconstruct where to pick up from that has been lost to the mists of time? And so that's the next, 20 years of work for all these disciplines.
I think I can help with this, and I better help straight away. Where Dirac went into the mist was he went into the mist with complex numbers. He assigned complex numbers to too many different things. Where a lot of science has gone into the mist recently is in thinking there's some sort of conflict between relativity and we've talked about that. And this thing, that's the point where people went into the mist, thinking that relativity and quantum mechanics were somehow in conflict with one another. They're not. One's a consequence of the other. We can talk more about this on Monday.
Yeah, let's do that. Let's do that for sure.
Yeah, that'll be cool.
But let's pick up there maybe.
Yeah, I think so.
And we'll get back to Martin.
Mm-hmm.
All right. Well, thank you so much, Dr. Williamson.
Pleasure talking to you both. Thank you both, doctors.
That's wonderful.
Everything goes well, and I hope you have a fantastic time tomorrow.
Thank you. Thank you.
Thank you.
I think we'll be in even better spirits on Monday as a result.
Good, okay. Monday it is. Monday at 6 o'clock. Take care.
All right.
Excellent.
Take care, sir.
Bye.
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 Have a good weekend.